at this time also. So, and so I will not take much time to welcome Professor Wilmani for his lecture. Okay, thank you, sir.
Thank you very much. Thank you. So, welcome back. Today mainly we will discuss some results related to fixed point theorem related to what is called non-expansive mappings. So, you already seen what is non-expansive mapping and many even algorithms. So, Professor Varende has discussed. Again, just before starting, okay, any doubt? You are welcome to ask. Otherwise, just I will recall one simple day-to-day thing we use in solving either finding roots of some polynomial or even transcendental equations like that. I will just quickly recall, then we will come back to non-expansive mapping. See, yesterday also, the last lecture that Professor discussed, we have a function. How we arrived at this function? I mean, even if we want to, let us say we want to solve, say fx equal to, now in fact, artificially I know that it going to root is 1 or 2, just to illustrate. So, see, this is my, this will not be, so x squared minus 2x minus x plus 2, we want to find an x so that this is 0. Then this will not be known, otherwise it will trivial, we know already. Just to formulate the problem I wrote that, just to illustrate. If you want you can put other cos x, sin x or any other thing. So then what we will do, this simply, that is now rewrite 3x equal to x squared plus 2 or x equal to x squared plus 1 by 3. This is what? Gx. Okay. So we have from the original function fx, we have got a new function that is gx. In this case, symbol 1, x squared plus 1 by 3. Yeah. Sorry, again. 3x plus, yeah, thank you. So that is our gx. That means, what is the relation between gx and x? We want to find on x such that this is gx, this should be equal to x. So that's what we are trying to find on x, that is find on x in a suitable, in this case anywhere in R, find an x in R, find on x in R such that gx equal to x. For that we want to see whether we can use our node, that means we are finding whether there exists a x such that gx equal to x. We want to see whether it has a fixed point. Even if it has infinitely many fixed point, fine. We know that we start with the polynomials, it cannot have more than 2 roots. So then this is what the reason. For that we will write under suitable condition, then we will start with any initial point. I will come back. X naught is initial point in some suitable place. Initial, start with x naught, the next step is x1. That's what we call it. x1, what is x1? G at, we are at x naught, apply G at x naught is x1 and x2 is G at xn, like that by induction xn plus 1 equal to G of xn n1 to 3. See, we get a sequence xn. Will it converge? Suppose it converges. Then what will happen? If the function also, suppose xn converges to x. Suppose we are telling, then will xn converges to x and g, that is, it is a continuous function. Says suppose if you are, this g is continuous, then xn converges to x imply again xn is a sequence in our metric space domain and x also in the same metric space x. Xn converges to x in our metric space, g is a continuous function from x to x, then g of xn will converge to gx. That will imply gxn converges to g of x. What is g of xn? That is xn plus 1 converges to gx. So what is this sequence? Start from x1, x2, x3 converges to x. What is this sequence? N equal to 1 mean x2, x3. I mean, you don't, it is almost same sequence. Okay, we don't get to subsequence, it is subsequence also. That converges to gx. And we should know that our space, suppose you are in a topological space, some other where xn may converges to x, it may possible, it may converges to some other element also. But our if you are in a metric space, host of sequence, it may converge or it may not converge. Converges means the limit is unique. So xn converges to x, xn plus 1 converges to g of x imply x equal to gx. That means we find a root. It doesn't, then how to, it shows there exists. Then that's what, then we will find a starting initial point, then how mod xn minus x naught is less than epsilon for a given epsilon, find a stage approximate. That is what they do in numerical analysis. For that how, but under all we have just assumed that if xn converges to x. So for that what is sufficient condition is, we will give a sufficient condition. These are all right, any standard book right from MSc level or even undergraduate we study. See, our function is g. Suppose g, a function from closed interval a comma b to r is such that g is differentiable. What do you mean by differentiable at the end point? They use familiar, no? If you want, we can take a open set containing closed AB also, then there it is. But I mean here that case, we are only at the left limit of, here the neighborhood of A means, here talk about only one side, here only closed A, this side some A plus something. Okay, this you can read. So we assume that it is a differentiable function, g differentiable for every x in the closed interval a comma b, and there x is k 0 less than or equal to k less than 1, such that modulus of g dash x, derivative of the function g at x less than or equal to k for all x in the domain. Suppose this condition is satisfied, okay, for all x in that domain. Then do you know any? Now we have closed interval a comma b, take any xy in the domain. Say that xy belongs to closed interval a comma b, x less than y. Now use mean value theorem to this closed interval. What is mean value theorem? The function is continuous on the closed interval, differentiable on the even open interval is sufficient. That's what even there we can relax. So all the kinds by mean value theorem there exists. By mean value theorem, there exists a point C belongs to a. Now we are applying mean value theorem to closed interval x comma y. In fact, there exists xy belongs to xy such that f, our function is g such that gx minus g of y, y minus x, because y is greater than x, our assumption, okay, equal to g dash at some c, correct? I written correctly. That is mean value theorem. Any doubt? Now take modulus. This implies modulus of this. But what is this? Less than or equal to k. Hence this implies modulus of gx minus gy less than or equal to k times mod x minus y for all xy in the domain. Okay. So then you will, that means the map is a contraction map. So you have to find suitable condition on which interval. G is a map from closed interval a comma b to closed interval a comma b. Why you need closed? Because complete metric space. In fact, interval need not be, but here, but to use mean value theorem, to use Banach contraction theorem, we don't require interval, enough to have complete metric space. That means any closed subset will do, but to use mean value theorem, we need a closed and bounded interval. That's why we have taken this. So that's what. Hence, under this condition, now start with any x naught. Start with any x naught belongs to a comma b. Then we do not know where ultimately it will converge. Then start with the x1 equal to g of x naught, x2 equal to g of x1. Then because of Banach contraction, this Picot iteration will converge us to some x. That is our fixed point. That is our solution of the started equation. See that, let's say for example, there what we start, x equal to x squared plus 2 by 3, correct? See for example, this is our gx. Here even the whole, everywhere it is differentiable. G dash x means 2x by 3. See, will it be, so modulus, okay, even less than or equal to 1 where less than or equal to k for some 0 less than k less than 1, for which will it be true for all x? In this case, modulus of g prime of x equal to 2x by 3, we want that should be less than or equal to some k, and k should be strictly non-negative, strictly less than 1. Okay, positive also strictly less than 1. See, even at x equal to 3 by 2, it will be 1. It will not be so. Where it will be, we should be, suppose x should be less than 3 by 2. So, now then we can find a k satisfying these conditions, say close 0 to some alpha, where alpha is strictly less than 2 by 3 or 2 by 3. Or you can fix some number. Now you start any x naught in that interval. And also you have to check whether it is a map from x to x is here mean that I have not checked, you check. Well, then only we can apply. It should be a self map. It is suppose G is a map from close AB to some R, not a self map, then we cannot apply Banach contraction theorem. It should be a self map such that, and further it is a contraction map, then the iterative sequence will converge to a point x, and that is our fixed point, that is a solution. These are all elementary, just yesterday sir was discussing, just to, that is essentially application of Banach contraction theorem. Someone asked whether we can use any theorem you can use, but you have to check whether all the conditions of the theorem will be satisfied or not. Suppose you are using, say, for G you are using, which suppose you are using Condon map, then G need not be continuous. Suppose it is not continuous. You are getting xn converges to x, you can get, and that is fixed point. Can you write there using some other way, using that contraction we can prove that Gx equal to x. But you cannot, using continuity you should not say that xn converges to x, Gxn converges to Gx. You have to use the definition of that contraction, distance between Tx Ty less than or equal to k time distance between x Tx plus distance between y Ty, k less than half. You have to use that condition. Here we have the advantage, we know it is continuous, so we can use it. So before using any result you have to check. That's why here I did not want to check. You can, if it is a self map, yes we can use. If it is not a self map, we cannot use. You can see any number of example you can check. This is just to illustrate or what is the iterative method for solving, finding even roots. And normally what even we will see that how to select at one point it is negative, one point it is positive, that there is a root. Then that way, then that is a self map, or I mean all those conditions, self, which interval. At one point, I mean f at A, f or G, whatever, G at A, G at B negative, then there is a root in between. So like that, then we select, then it is a self map, and whichever theorem we want to use, check whether all the conditions are satisfied. Okay, now we will start something new. This is a little advanced. Advanced is okay. What is Banach contraction theorem says? X is a complete metric space, or say X is a complete metric space, capital A non-empty closed subset of X, and T a map from A to A, and if it is a contraction map, it has a unique fixed point. That's what is, this contraction condition is very strong. Then we have seen example also, even under next what we have seen is, even with the, we have discussed some what is called the unit ball in R2, I mean what is our set A, or call it K, set of all X in R2, so that norm we use, so length of the vector less than or equal to 1. Then take any point x belongs to K, rotate through a fixed angle, fix that angle theta, or that's all, either you take pi by 2 or pi by 4 something. Rotate through a fixed angle. First, if you are x naught mean if you rotate, so it will go to this point, again rotate the same angle, that is x naught, x1. Suppose if you call this way, where it will be? It will only moving along here only. If it is x naught, Picard's iteration. See, if it is rotate the unit ball, center is origin. If you rotate through an angle, say pi by 2 or pi by 2, let us say, first, will it have a fixed point? Center is this, you are rotating this. So this point after some 45 degree or 90 min, 45 min, it will stop here. Again 90, then 90 plus 45, 90 plus another 45, like that it will full circle. Okay. Again a point need not be for every point may be on the unit sphere or maybe inside everything. Okay. Will it have a fixed point? No fixed point. Center is, we have fixed this point. We are rotating only this axis where this is not moving. Center will not move. Yeah, we can write the equation. The point is any point r x r e power I theta. Then we are rotating e power I theta, image is e power I theta plus some pi by 4 or whatever fixed element, then you can use that, you can formally prove that it is in fact non-expansive. This was Professor Berende also discussed. In fact, that's why in this case also, if you take any point including here, this is x naught, if you are rotating, this is it goes to here. Now this is image of that point. Now take this Tx naught, T from K to K, the rotation, take the midpoint. What is midpoint? X naught plus Tx naught by 2, midpoint of this, that you call it x1, not Tx naught equal to x1. This is our x1. Now again you are rotating, this x naught will go to next T of x1, then again find the midpoint of that, that is this is T of x1, then x2 will be, call it x2 equal to x1 plus Tx1 by 2. Geometrical also you can see then the midpoint, then keep going, then it will approach us to the origin. In fact, later that's what that iteration is called Krasnov-Sulky iteration. When more generally for given x, image is Tx, x naught, x1 is, if you want you can have lambda x naught plus 1 minus lambda time Tx naught. Here lambda equal to 1 by 2. That's what that. So this is just to illustrate that the Picard's iteration, start with x naught, define x1 equal to Tx naught, x2, Tx1 like that by induction, that always need not converge to a fixed point. Only in the contract, if metric space complete, the contraction is very strong, then it happens. Otherwise, then this was introduced by, in 1965, for Prouder, Cochrane, I don't know, later Kirk. All are in the same year. Prouder first proved it for a Hilbert space, H Hilbert space, or you call it X is Hilbert space. X is our Hilbert space. K non-empty always will take closed, bounded, convex subset of our Hilbert space X. T from K to K such that it is non-expansive. The distance between, why contraction means distance between Tx, Ty contracts strictly less than or equal to K time original. Here it will not contract, it will not be non-expansive, it will not be more than distance between xy. It may be equal such that distance between Tx, Ty, but what distance between Tx, Ty we write in nonlinear space? Norm of, what is the metric? X is a nonlinear space, d of xy we define as norm of x minus y equal to norm of Tx minus Ty less than or equal to norm of x minus y for all xy belongs to K. K is just, it's a closed bounded convex set. But we know, is it compact, closed bounded in a finite dimensional space? Closed bounded set is compact. So if our Hilbert space is finite dimensional, it is compact. Then it will become compact as well as convex. And if it is non-expansive, that will imply it is continuous also. Then that is what Sauder fixed point theorem. What is Sauder fixed point theorem say? Sauder is, K compact convex subset of a Banach space, we will take Banach space, T from K to K continuous, then there exists x in the domain so that Tx equal to x, it has a fixed point. That is even identity map is satisfies all the condition. Even non-expansive map also, every contraction map is non-expansive. Non-expansive need not imply contraction. We have seen yesterday also the unit circle, we defined Tx equal to what we example yesterday we discussed. If we take the unit S1 we call it, set of all x in R2 say that norm x equal to 1 unit sphere. Then if we take any point x, the image Tx is minus x. Then we have seen that norm of Tx minus Ty equal to norm x minus y. That means distance between Tx, Ty equal to distance between xy. That case we call it is an isometry. Isometry we mean we feel that exactly this and this set will be identical type feeling. But this map does not, it is an isometry. The unit circle is compact, closed and bounded subset of R2, compact, that is why I told it is connected. Unit circle is connected, compact, connected, T from K to K, isometry, it also, that means non-expansive also, but it does not have any fixed point. That is why what is important is the convexity. Without further we assume that it is convex. Suppose unit what is the smallest convex set containing the unit sphere? Smallest, you heard about the name? Suppose 1, 2 in R. What is the smallest convex set containing 1 and 2? Pardon? Smallest convex set containing real number 1 and real number 2. Geometrically you can, pardon? Correct. Line segment between 1 comma, that means closed interval 1 comma 2. That's why there no difference between connected and convex. So here what is the convex set containing this unit circle? Huh? Unit ball. Okay. Here we sometimes what you say is correct. Some places sometimes we use unit sphere even for the set of all x as the norm x less than or equal to 1. Here we take unit sphere set of all x norm x equal to 1 boundary less than or equal to 1 unit ball. So because if you take any 2 point, all these things will be there. You cannot remove the so unit ball you have to go. So convex, you see, further assume it is convex, then we can prove. Again, this we are going to prove for any Banach space. Here to start with this Hilbert space. Finite dimensional means no need of proving, already there. Prover's theorem, then infinite dimensional also Sauder fixed point theorem. So what is important here is, it is just a closed bounded convex set. Okay. Yesterday also someone suggested the first day, then very natural thing is, first can you give at least one example, say that it is a closed bounded convex set but not a compact set. Closed bounded convex set but not compact. Can you give an example? In a Hilbert space, because we want to start with a Hilbert space. Later we will see for other thing also. That's what if you have revised functional analysis, it will be still easier. Even metric space knowledge will do. Close, what you know that we know only one familiar infinite dimensional Hilbert space. Which Hilbert space we are familiar? More familiar? Which Hilbert space? Any one example? Pardon? Example of a Hilbert space. Finite dimensional even R is also, R is a Hilbert space, set of real number. R is a, what is inner product x with y? What is, don't say escape, usual. It should not be useful answer, no? Equal to what? Inner product, suppose order pair x1, y1, one element. Order pair x2, y2, then inner product is of these two elements. x1, y1 plus x2, y2. Okay, like that we know Rn. If it is vector space over R. Suppose if it is R itself. Just product. X in R, y in R, the inner product nothing but there x into y. Now in the beginning start y, the inner product means is x1, y1 plus x. There we start with x1 real number, y1 real number, x1, y1. Okay, that Rn we know. That is inner product. That inner product will induce a norm. You can verify standard dot product. How? What is that norm? No, not in R alone. General inner product space. X vector space over R or C. Let us take over R, real vector space. So we know what is an inner product. Inner product, no need of recalling, no? Okay. X is X with an inner product is there, inner product space. That will induce a norm. What is that norm? Norm of X equal to using inner product. Using positive root of inner product x with x with x. If we go for even R2, we see that what we mean by when y equal to x, order per x1, x2, order per x2, y2, then dot product is x equal to y mean again x1 squared plus x2 squared, that is nothing but Pythagorean distance or Euclidean. So we can feel it, then we generalize. So motivation come from symbol like either go to R or R2, then we will extend. We know that if X is an inner product, then we define norm X for each X in X, positive root of inner product X with X, then we can prove that it is a norm, and this norm is it always, will it be, whether it is complete? Every inner product will induce a norm. When that norm will induce a metric, d of xy equal to norm of x minus y. From vector space we define a vector space, we know addition and scalar multiplication having some property. Then we have defined inner product. Okay, that will give the additional thing. So we can give the length as well as even angle between two vectors, all those things. Okay, now we got a norm, inner product. The next one, what is the question? Whether it will induce a metric, whether that metric is complete. That means whether every inner product, what do you mean by every inner product is complete? Mean the inner product will induce a norm, whether that norm is a complete nonlinear space. Is it true? I am making this statement, every inner product space is a complete metric space. Say true or false? False. Then someone else. Give an example. Suppose X is, because we are more familiar only finite dimensional, then what will happen? If it is finite dimensional, then it is true. So, to give an example, that should all these things, functional analysis, all this advanced fixed point theory, all meaningful. If we cannot stop only with finite dimensional, you have to come up infinite dimensional. So then only it will be more useful. So can you give an example of a inner product space which is not complete? Even if you know an inner product space which is complete, from that also we can get a. Okay, can you give an example of an inner product space, infinite dimension which is complete? Either you give inner product space which is not complete, or give an inner product space which is complete. Familiar one is L2, little L2, capital L2 will, that is using measure theory. So first again we will call it capital X. This is very important. Each element is a sequence of real number xn n1 to infinity, so that each xn belongs to R, n1 to infinity, square summable, mod xn square n1 to infinity is converges, that is all. This is useful, converges. Okay. What is the here? This is our set X. For x1 element in L2, y another element in L2, what is inner product x with y? Summation n1 to infinity in this case. What is, see, finite dimensional means x1, x2, xn, n double, y1, y2, yn. There x1, y1 plus x2, y2 plus xn, y1. Here we will not stop. Summation, yeah, xn, yn, n1 to infinity. Whether it is meaningful to write this? I have written some summation xn, yn, or you call it xn, yn equal to an. So you call it summation n1 to infinity an, where an equal to xn, yn for all n. Xn real number, yn real number, so xn, yn is a real number. So what we got? Square also. First we are writing this xn, we want to check whether this is meaningful. Summation n1 to infinity an is a series. So, but inner product is what? It is a function from x cross x to real inner product R. So, that means image x is one element, y one element, inner product x with y we are defining as summation n1 to infinity x and yn. That should be a real number, that should not be infinity or minus infinity, it should converge. Why it converge? You have to verify. So, you heard about, for these things are all non-trivial. While proving that there are some inequalities like Holder's inequality, using that Minkowski inequality, all these things, even to prove that it is a vector space. Later, see, we are directly writing, we also have to define x, L2 is only a set. Before proving, defining inner product, you have to verify that it is a vector space. Vector space, I mean again we will not spend more time, x equal to xn, y equal to yn, then component wise, x plus y equal to xn plus yn, again alpha times x is alpha xn, then we have to verify that it is a vector space. For that itself, you have to, x is in L2, y is in L2, then you have to prove that x plus y again L2, that will be easier. Then while proving norm or inner product, you need some other Minkowski's inequality, Holder's inequality, like that. Like Schwarz inequality in finite dimensional case. So, this you please go through. So, we know, we can prove that this is an inner product space. Under this, then the norm, L2 norm we call it, this is very important for us, norm x suffix 2, we call it summation mod xn square n1 to infinity. Here it is easier, mod x, x is in L2, that means summation n1 to infinity mod xn squared finite, this series converges, that means this is a real number. Real number means finite, fixed, positive real number. Then we can take the root. That is what the length of the vector x. Then you can prove that using Minkowski's inequality, means nothing but triangle inequality, but to prove that you need Holder's inequality, that it is a non-linear space, or you can satisfy parallelogram law, or from inner product you come, then we can prove that it is a complete metric space. So, that itself non-trivial. I mean, proof is not difficult. Again, component wise we will do. If you take a Cauchy sequence xn, here one xn is a superscript, x1, x2, I mean the sequence will be x1, one element in L2, x2 another element, like that. So, x1 means, we write it x1 1, x2 1, xk 1, kth element, like that. x2 means x1 2, x2 2, like that, xk 2, like that. Like that here nth term and mth term and distance between xn and xm. That means then you will prove that each component, this column, they converge, because we are, if you start with the Cauchy sequence, then we will prove that for each fixed k, the kth column, xk1, xk2, that is a Cauchy sequence in R, that converges to an element xk. So, like that you will get x1, x2, xk dot dot. Then you have to prove that that is in L2, and the original sequence xn converges to this x1, x2, x3. Same idea will use whether it is in L2 or LP, 1 less than or equal to p less than infinity, L infinity. Okay, what is L infinity? For us, these two things more important. L infinity instead of this, just it is a bounded sequence. Then what is the norm there? There it is not a metric, norm. It is a metric, it is not an inner product. Note that inner product space will induce a norm, the norm will satisfy which law? Parallelogram law. Like L infinity, even 1 less than p less than infinity, they will not satisfy parallelogram law. So inner product will become only when p equal to 2. That is complete, that is Hilbert space. So, but L infinity norm is, that's it, supremum mod xn. Why we can take the supremum? Because it is a bounded sequence. Again we will go back to a bounded sequence, means it will have upper bound. It has an upper bound, lower bound. Here what we are interested is upper bound. Set of all mod xn, n 1, 2, 3 has an upper bound, hence by which axiom? One of you. LUB, least upper bound axiom. If a non-empty subset of R has an upper bound, then it will have least upper bound, that we also call supremum. Hence the supremum exists. This is simple exercise, including to prove triangle, no Holder's inequality or Minkowski inequality, then it is a nonlinear space. Again it is complete. Complete also again the same idea will use. X1 it will be a sequence of the one element, mean one element in L infinity mean a bounded sequence. Then again like that, then each column you prove that it is bounded. That is almost simple. Each column, kth column is bounded and you will prove that if you assume that xn is a Cauchy sequence, mean again each column is a Cauchy sequence. Then we are in R. That's why completeness of R is at least that proof, that's why I repeat it even second time. R is complete, then each column will converge, then you will get x1, x2, x3, then you have to prove that that is bounded, hence it is in L infinity, then xn converges to that x. So hence L infinity, just some idea. So the reason I will tell why we are interested in these two spaces right now. Okay, now come back to our, now we are comfortable with L2 to start with. L2 is a Hilbert space, you can verify, it is a Hilbert space. Okay, now take the unit ball, whether unit ball is set of all x in L2, so that norm x of x2, sometimes we may just say norm x, L2 norm, less than or equal to 1, the unit ball in L2, that is closed, bounded, convex. So far our condition will be satisfied, closed, bounded, convex, whether it is compact. That's why giving example is not difficult. Closed bounded convex subset of L2, unit ball, for that matter, any closed unit ball in L2. Is it compact? If it is compact, what will happen? Oh, that's correct. We'll come back to that. Some non-expert, okay. Some student function, no. What you are telling is correct, example is correct. So even without you using that also, unit ball become compact in any nonlinear space. Suppose the unit ball, set of all x in the nonlinear space x, such that norm x less than or equal to 1. Suppose that set is compact. Then what can you say about the vector space? What type of vector space? It is, dimension is finite, that is using, that is called Heinz-Borel theorem, that is functional analysis like Rn type. Finite dimensional means essentially it is isometrically isomorphic to Rn, it is like Rn type. I mean you can prove any finite, once the unit ball become compact means the vector space will become finite dimensional, because functions maybe some of you will study little later, third semester students. That at least keep this in mind. If you are here, that's what if you have any infinite dimensional vector space, there we have a norm. That means infinite dimensional non-linear space. Then the unit ball will never become compact, but it can become compact in some other sense. We define what is called weak topology. It may be compact with respect to weak topology. Weak topology, it may be little involved. The smallest topology on the nonlinear space X, which makes every f belongs to the dual space continuous. We call tau omega. That is the smallest among all topology. Norm will induce a topology that is with respect to that every f is continuous, f in the dual space. Dual space means set of all continuous linear functional. That is there. But there may be many norms. Among the norm, we have to prove there exists a norm which with respect, that is the smallest norm which make every f in x prime also continuous. That topology is called weak topology. Suppose a set is compact with respect to that weak topology, we call it weakly compact. Finite dimensional, there is no difference between compact, weak compact and compact with respect to the norm, topology induced by the norm. Okay? This here doubt mean you can ask, please ask. This is little for students first time in. Any doubt? Pardon? Okay, first I will give you a simple application using Banach contraction theorem, then we will come back to our stated theorem. K closed bounded convex subset of a Hilbert space, T from K to K non-expansive, then it has a fixed point. That is called Prouder's theorem. Later Prouder and Koch, they proved the same theorem in place of Hilbert space. They assumed what is called uniformly convex Banach space. Okay, that I will explain, it depends upon the time. And the same year, Kirk introduced a concept called, he did not introduce the concept normal structure, that was introduced by Brodsky and Millman in 1948. Brodsky and Millman in 1948 introduced a concept called normal structure. See, normal structure means, see, suppose we are, okay, now suppose set is like this, convex and everything is here, symbol set I will write, okay, like this, need not be unit ball. You take a point here, any point, this is our set K, x belongs to K. From x is fixed. Then this we call it R of, sometimes the small r or capital R does not matter. X is fixed, then find the, from x find the distance to every point. Every point from here means everything is there. That means supremum of norm of x minus y, y varies from K. Okay? This we define for, we can define for every x. Why this supremum? Whenever you write something, whether it is meaningful, supremum x is fixed. See, I am here, say, I am x. From x to every one of you, I am finding the distance. Then I can find the maximum distance because finitely many. Here, our set may be not finite, it is infinite convex set. Why supremum x is? Because our set K is bounded. Because of bounded, norm of x minus y less than or equal to some constant. for every. So it has a upper bound, supremum will exist. I think in the beginning, for whatever we write, whether it is meaningful or not, we'll check, then proceed. So supremum exists, and what is the diameter of the set? Diameter of K equal to supremum of, what is the, how we define diameter? Distance between any 2 points, then take the supremum. We should not tell maximum, because maximum no meaning if we do not know it may exist or may not exist. So this diameter of K, supremum of norm of A minus B, say that A comma B belongs to K. This also exists. Sorry. It may happen that what you feel that R1 for each x, see, even a simple thing you take, closed interval 0, 1. Our set K equal to closed interval 0, 1. I am taking a point, say let us say half. What can you say about delta of half and K? That's why I tell you first, even the teacher doesn't have time to spend so much time, because you have to complete the syllabus, to do so many examples, extremely simple. See here what is our this say, in this case our x equal to half, y varies from where? Y may be this side or this side, anywhere. What is the maximum? In this case maximum x is supremum. What is that? Delta of this is equal to half. What is the diameter of K? Diameter is 1. So half is less than 1. That means, suppose if we take the point itself 0, suppose x is 0, what is delta of 0 comma K? 1. That is equal to diameter of K. Okay? But there are points, in this case enough point, any interior point, there is an x, so that delta of x comma K is strictly less than diameter of K. See, essential idea of this is what the geometrical structure introduced by Proudski and Millman to prove some fixed point theorem, not in 65, 1958. They proved it, the family of isometry map. Each member in that script F, a collection of map from a weak, okay, you take it easier mean closed bounded convex subset of a, say, Hilbert space. But Hilbert space we should not use Banach space, because Hilbert space we can prove that it has normal structure. So you can take X Banach space, K compact with respect to weak topology, K some type of compact, or even you assume that it is compact, K compact convex, script F a collection of map from K to K, such that norm of Tx minus Ty equal to norm x minus y. Every map there it is an isometry map. Compact convex, we have a family of map, and then under want to see that can we find a x in K, one point which will preserve every element in, that means there exists x in K, such that Tx equal to x for every T. Suppose T1 is in S, T2 is in the collection script F, T1x equal to x, T2x equal to x, T3x equal to x, like that. Common that family will have a one point which is preserved by, fixed by every member. So that type of result long back, that's a Proudski and Millman proved. That using that time they introduced normal structure. You can easily verify that, not very simple, it is not, if it is a compact convex subset of a Banach space, yes it has normal structure. Meaning is, you take K, I will not write everything, K, now we always assume that closed, bounded convex set. This has normal structure mean you take any f subset of k. Again f is closed bounded convex. I mean, so already it is subset mean it is bounded, so that means closed convex. F closed convex, non-empty also, closed convex, F closed convex implies there exists at least one x in F. See, this is our F mean, we will get an x from here, then that delta x F strictly less than diameter of F. That is there exists x in F, so that delta x F is strictly less than diameter of F. If such a x exists, it is a non-diametral point. It is not equal to diameter of the set, so it is non-diametral point. And I purposely I did not write any non-empty alone I wrote. Will it be okay? You have to tell that if you are doing some mistake or some error, writing error or anything, you should tell. So you have to put any other additional condition. F is any closed convex subset of K, non-empty. Then it should have a non-diametral point. That means there exists x in F, so either delta x F strictly less than diameter of F. This will be meaningful? Suppose this is our definition. Can there exist an example of a set which having that property? For a trivial set, diameter of delta x F equal to always diameter of F. When F equal to, for which F, if we take F, some very simple example, delta x F equal to diameter of F. What is that F? F is, we want closed. We are in a Banach space. Every singleton set is closed. Singleton set is convex. Singleton set also take 1 minus xy. Xy in F, F is singleton x means only one element, only x is there. Then 1 minus tx plus t, y equal to x. That means that is again x. Singleton set is convex, it is closed. What is the diameter of? Diameter is 0. What is delta xf? 0. So, whether can we get strictly less than 0, strictly less than 0? No. So, we have to, that is why while giving definition you should be careful. So, what we have to add? We have to put that restriction, not just non-empty. It is a non-empty closed convex set containing more than one element. Yeah, at least two element means once it has two element, it will have infinitely many element also, because convex set. Once xy is there, convex combination. Otherwise, diameter should be positive. So we have to, that's why there exists F is closed convex, diameter should be, see sometime while writing, that's why not prepared note. So we writing by, just we may miss it. Not that not knowing, we may writing error. So you should be careful. So what is important? It should contain more than one element. Then every set should have a non-diametral point. Then such a set K is called has normal structure. Then we can prove that every compact convex set has normal structure. In a Hilbert space, again Hilbert space means what you have to think immediately? Your Hilbert space means which law? Parallelogram law. Use parallelogram law to prove that every closed bounded convex set has normal structure. In fact, little advanced is, more general is what is called uniformly convex Banach space. For us enough to it is not difficult. Take any closed bounded convex set containing more than one element. Then it will have a don't just take any closed bounded convex set, diameter of that set is finite. In fact, take an interior point. Then that you prove that that is a non-diametral point. Use only parallelogram law. Just parallelogram law, use that and then you can prove. That is, so motivated by the result, more than result, the definition of normal structure, instead of Hilbert space, Crowder and Cockday, they proved for uniformly convex Banach space. Okay, that again that is like something in a finite dimensional space mean the first day also I told it is like this. We are in a finite dimensional space mean x is on the unit sphere, y is on the unit sphere, the midpoint will not be there. Motivated by that result, Kirk proved this following result: K x Banach space, K non-empty, weakly. Again you are not comfortable mean instead of weakly compact, think of compact. Yes, it is compact. Only topology is, we get not the topology induced by the norm. Topology induced by the weak topology. I mean induced by the smallest topology on X which make every F belongs to continuous. Weakly compact, convex important. T from K to K non-expansive, that means norm of Tx minus Ty less than or equal to x minus y for all xy belongs to K. Kirk 1965, weakly compact T non-expansive. Further, that is what important. Further, K has normal structure, then it has a fixed point. Then there exists K such that Tx equal to x. Okay, this is more general than the result of Crowder and Cockday, because uniformly convex space means every closed bounded convex set is in fact weakly compact. If you have a reflexive Banach space, uniformly convex Banach space is reflexive. Reflexive means what? The canonical embedding is onto. Canonical embedding you heard? Familiar? No? Okay, just quickly I will again will not go in detail. See, X is nonlinear space. You know what is the dual X nonlinear space? What is the dual? Set of all F from X to R, F continuous and linear, we are in a vector space, that is the dual. Again this is norm. Now for each F in the dual space, norm of F equal to supremum of mod Fx such that norm X less than or equal to 1. Okay, that we can then dual space will become a nonlinear space. In fact, it became a Banach space. So we can talk about the dual of that dual. Okay, so that is called second dual. I mean there is an isometry between X and isometry means not just any map. We define a particular type of map that we call it canonical embedding. So we want to define a map from X to the second dual. That means what? Fix X in X. The map which we call it X goes to Jx, but Jx belongs to here, it should belongs to X double prime. That means what? It is a continuous linear functional from X prime to R, because our now in place of X, X prime. I mean Jx, X is fixed, define j suffix x from x to functional to R, vector space over R, as what is the natural way? J suffix x, f belongs to where? Sorry, here it is dual. J f. F is this L. F is where? F belongs to first dual. X is where? In capital X. So X is in X, F belongs to X prime in, this implies F is a function from X to R, which is linear and continuous. So X is here, then what you, which element you can get? We have only F is there, X is there, then how to get a real number? Fx, that is the, so that is Fi. This way we define. This is in R. That means in a natural way, that's why it is a natural embedding. For each x, Jx is a map from x prime to R. Then we have to prove that this is continuous and linear. Using Banach theorem, we can prove that norm of Jx, what is? Somebody. Norm of Jx equal to norm of x. It is a linear functional, bounded linear. Bounded mean, you know, a linear function is bounded mean norm of Tx less than or equal to some constant time norm x. So for all x, for a fixed alpha positive. Then we can prove that in fact it is all. So can we say it is an isometry? For each x, Jx belongs to second dual. X is in capital X. For each x we define Jx. Jx from x prime to R defined as J suffix x of f equal to fx. So then you prove that this is again continuous linear functional, hence it belongs to the second dual. And Jx equal to norm x, you can prove it. Norm of Jx equal to norm x, hence it is a onto map. Hence every onto mean you are going to call reflexive. So every space is going to call something, everything is going to be reflexive mean. See simple inclusion you have studied above. See I am defining a map. Closed in the some, see it says that for every x, fx equal to mod x will imply it will, still we cannot say it is on to. See inclusion for up to there, see we have the map for given, there it is R in this case, x is here, for every x, Jx norm of that is 1, but that need not be occupy the whole place. Norm Jx equal to x, but J need not be, this is what is important is, okay, that, so we have a map J, not Jx, we don't want Jx, Jx is only second dual, J of x, you take an element x here, then J of x equal to x goes to Jx. That means J of x equal to J suffix x in the image of x. That map if you call it T mean Tx equal to J suffix x belongs to second dual. So this will be, see in vector space, if x is vector space, y vector space, T from x to x, suppose it is 1 1 linear map, x finite dimensional, when 1 1 will imply onto same dimension also, x to x also you take, T from x to x, it is 1 1, this will give you it is 1 1, but 1 1 imply onto when finite dimensional you have to, kernel rank plus nullity theorem you have to use. Okay. So only finite dimensional mean yes it is onto, correct. But if it is infinite dimensional, it will be 1 1. You can prove 1 1. Need not be onto. Suppose this map is onto, this canonical embedding is onto, then we say that the original space is a reflexive Banach space. There are many characterizations. One mathematician called James, many characterizations are there. A Banach space is reflexive if and only if the unit ball set of all x such that norm x less than or equal to 1 is compact. With respect to, compact mean it become finite dimensional, but we don't want infinite dimensional also. If you want to take compact with respect to weak topology, that's why that is important. Compact with respect to weak topology. So here there are some nice open problem. This we will discuss in the next lecture. In just I will take in 5 minutes. I will simple application of simple theorem. This also will prove using Jones lemma. What we will do? Prove, collect all the invariant sets, closed, bounded, convex subset of K. Say all F closed, bounded, convex set. T of F is subset of F, F non-empty. Collection of all invariant closed convex subset of F, then use Jones lemma. F1 less than or equal to F2 means F1 in subset of F2, like that. Then Jones lemma, it will have a minimal invariant set. Then we will use normal structure. Every closed bound, if it contains diameter is positive, it will have a non-diametral part. It is invariant set. Invariant means what? T of F subset of F. That subset F is singleton means what? X is in F, Tx also in F, but Tx contain only one element, so Tx will become X. That is the idea. We use Jones lemma, we get a minimal invariant set. In general, the minimal invariant set need not be a singleton. If it is singleton, we are through. Otherwise, the set has normal structure will imply we can find another proper subset, say F naught, a proper subset which is closed, bounded, convex, invariant is a proper subset. That will give you a contradiction. For that we need normal structure. We will see how we will use that also. That will give you a contradiction. That is the idea of normal structure. In fact, we do not know what is open problem here is X is reflexive Banach space. The canonical embedding is onto. K non-empty, closed, bounded, convex set. T from K to K non-expansive. See, I will write it again. Because K non-empty, closed, bounded, convex, subset of X a Banach space. T from K to K non-expansive. I mean again norm of Tx minus Ty less than or equal to norm x minus y. Then if we do not assume K as if K as normal structure, yes it has a closed bounded convex will imply weakly compact in a reflexive space. Okay. So non-expansive, if we do not assume normal structure, whether the question whether there exists X in K such that Tx equal to X is not known. Meaning is what? Nobody knows. That means not true means you have to produce a counter example. You have to give a reflexive Banach space and give a closed bounded convex subset of that Banach space, reflexive Banach space, and define a map T from K to K non-expansive and prove that it no fixed point. Okay? Nobody knows such a thing exists or not. Right from 1965, there is some partial answer is there given by in 1981 or so, that is for weakly compact. If it is weakly compact convex and T from K to K non-expansive, then it need not have a fixed point, is somebody settled in somewhere in 81 in proceeding AMS. That again I will mention about that. So this is open. What is other important thing is, again a simple functional very classroom exercise. L2 is a Hilbert space we have seen. Have you heard about re-norm? Equivalent norm. See, vector space on R2 how many norms we can define? R2 itself. That's it. Again go for simple example. X equal to R2, order pair xy, norm x, this suffix to norm of mod x square, I mean root of x squared plus y squared. What is L norm? Order pair here either xy or x1 y2. The L1 norm in mod x plus mod y, and norm x. There are infinitely many, so that is maximum of real number, so we can write mod x mod y like that. Okay? These are all norms. Any relation between these norms? Simple, you might have heard. We can find, so let us say which one you norm 2 and say norm 2, the exercise, find alpha beta greater than 0, say that alpha time norm x, norm, okay, here we are using order pair xy, suffix 2 less than or equal to norm of order pair xy suffix infinity less than or equal to some other beta times norm of order pair xy suffix 2 or 1. We are comparing L2 and L infinity. So here both again L2. Xy one element means we will write alpha norm x less than or equal to norm x less than or equal to beta norm x. Just write it this for all x in R2. X is in R2 in order pair. More generally any norm linear space. If their x is alpha beta greater than 0, satisfying this condition, then we say that these two norms are equivalent.
This is the condition for the equivalent of two norms.
Conditions for equivalent of two norms.
Topological equivalence also.
Yeah, meaning, yeah, as Professor Murthy pointed out, this imply if we have an open set in L2, the same set open with respect to the new norm also. Other way also. They will induce the same topology.
Yes,
they will induce topology is same. Topology is same. We have seen strictly convex. When a non-linear space is strictly convex means take a point on the unit sphere norm x1, norm y1, take the midpoint. Midpoint should not be on the unit sphere when x not equal to y. So they are equivalent norm, but norm, two norm, yeah, I will stop with over. Two norm, our unit ball will be like this. So if we take a point here, midpoint will not be, midpoint will be inside less than 1. But if it is L infinity like that, the some worse, either these are, check if it is like this, it can be here. X is on the unit sphere, y is on the unit sphere, but midpoint also on the unit sphere. That means it is not strictly convex. Finite dimensional case, strictly convex and uniformly convex, same thing. So they are all not Hilbert spaces. That means what? L2 is a Hilbert space. you can define a renorm it, the new norm, topologically they are same. Many topological compact there mean compact here, continuous there mean continuous, all those nice. Linear there mean linear, you don't need anything, only vector space. But geometrical structure will vary. X with L2, with 2 norm it is Hilbert space, infinity norm, L1 norm, not Hilbert space. So the question is, even if L2, if we renorm it, L2 will have normal structure, the renorm need not have normal structure, then what type of renorm if we have, then whenever closed bounded convex set, T from K to K non-expansive, it will have fixed point. Whether it has normal structure or not, such a renorm, some renorm of L2 will have, that we call it fixed point property. Such things are also, we do not know. So we will discuss in the next class. Thank you very much again for the, again please feel free to ask questions.
Yeah, very, I can say that innovative talk by Professor Veeramani. If you have any question, then okay. Otherwise what we do is, actually the tea is ready, so we take the tea. But I have question, Professor. Not only the question actually, it's a really an interesting part. The question is something like this. I did lot of work actually. Me and my collaborator UJ Cho, we worked a lot. And what exactly is this? We have this a non-empty set and have certain properties. I am not interested to disclose right now what is certain properties are, and we are defining, of course, the vector space, and over the vector space these are defined. So means vector space is there, of course. So we have the two norms. One is the norm 1 and another is the norm 2. Actually this definition we call it as the Sachs set.
It is something
you heard about this? Yeah, I did some work. And then finally it called as a Sachs spaces. Sachs space. Okay. So in this space actually we define these two norms. One is a Banach norm, another one is a Frechet norm. What actually yesterday Dr. Dhananjay Gopal was talking about, that is there is no triangle inequality. Of course is not there. Triangle inequality lies in one of the definition, and in another part you will find that there is another definition implies.
That means it is not matrixable.
Yes. So I was trying to find out, can we have two different norms? Can we have two different norms, means geometrically, and exemplary we can explain that we have two different norms, because we are successful in proving the Cauchiness. There is no issue. Our only the problem comes when we are proving the completeness and the convergence. For that we use one lemma, and this lemma is given in 1967. How do I pronounce this, Pathak or what you can say? He is not an Indian.
Oh,
yeah, he is not an Indian. Not Pathak. Pathak is my friend. So he is not an Indian. So this lemma we use, and what we do is we are just writing the equivalence of these two norms. I think she has done some work, right? So I don't know whether this girl has done or some other my PhD scholar has done. So we are using this kind of, the norm 1 is equivalent to norm 2, and finally what happened, in place of the two norms I am again coming back for the one norm for fixed points. That this is still open question. Still open question. I tried for the past 20 years, I am trying, not successful. So anyway, it's a renorming. I will discuss one thing, because there is a open session also. We shall discuss about such things. Okay, these are the interesting things, and anyone can solve. It is not restricted to that research scholar only can solve. even our students. I think this inequality, those who are in the MSc and MSc passed out student, they know very well that when we are talking about the finite dimensional non-linear space and infinite dimensional non-linear spaces, and you have the two different norms. My question is always among the students that how many norms you can define in a non-linear space? Tell me. And this is a 2 marks question, pattern question. And first day I will not tell. At the end of the class, a semester, I will say how many norms you can define. So I am always in a mood.
Each norm will carry 1 mark.
No, then full semester means 100 marks. So anyway.
And normalize.
Anyway, thank you. Excellent lecture by professor. And this renorming is going on. So I will discuss this also. I think it's a very good open problem anyone can discuss, and even once this is through, I think you can have a chance to go for PhD on this particular topic. Okay? Thank you. I will tell you later on what exactly the topic is called.
he tried to motivate all of us and giving many important suggestions. He is presently Professor, Department of Mathematics of Guru Kasidas University here. He has done, that's why now many students both in fixed point theory and data sciences and other related many interesting area, and he always motivate the students to do better work. In fact, that's what some 2008 I think, that's why one of the student is Dr. Uma. Some group of students, 10 MPhil students, to do their project work, he sent all of them to Chennai, then Madras. So they came to IIT Madras, visited the department, library, and went to other research institute, Madras University, Math Science, and other places at their level. Just they were doing MPhil. That going there and see some of the other people, what type of work, and mainly even to do talk with some research scholars and other students and do some, collect some good papers and then to do some good project. Like that he always motivate the student. So you all know better than me. So it is, I mean, we were long time friends, family friends. It is always my pleasure. It is my pleasure to welcome Professor Murthy to deliver this talk. He will be talking on historical results and their consequences after Banach, 1922, Kannan 67 and Jung in 76 and many other interesting results. So I request Professor Murthy to start.
Okay. Thank you, Professor Virumani. Thanks for very nice, affectionate and good introduction, and such introduction from an eminent mathematician like Professor Virumani is really, I am fortunate that he is here and talking about certain things, some issues, some results and motivation, philosophy, all such things. Actually, I intend to speak about that how the things are motivating us to discover some new ideas. That is what my thinking is. And at the school level, whenever any teacher says that mathematics is very hard, I feel very bad about it. That why they say mathematics is very hard and why they are not able to translate that hardship into the very easiest way, or I can say in a conventional manner to convince us. In such a scenario, when it was a chance for me to visit Africa, particularly the East African countries, and there I find that the people says that the hard and easy, what I realize, this is my purely my perception, hard or easy, this is all the perception. Of course, the hard things you need little bit more efforts, that's true, and you can make it easy. Sometimes you have to work for a long time to understand such concepts, and loving the particular I can say the person first, because the first person used to deliver the such interesting results, such interesting subjects. So unless you like the person, I also realize for the past 30-35 years of my teaching experience that it is difficult for us to decide whether the subject is hard or easy. There are many subjects, initial stage we feel is not easy, is very hard, and later on we realize that this is really a very easy task to understand. So this is what my journey. I will reflect this talk will reflect the results which I liked mostly. Like the Banach, when we say about the Banach, and I tried to organize one international conference were in a virtual mode in 2022. In 2022, I tried during April-May 2022 and thought to organize the conference before completion of the end of the 2022, and I tried to connect all over the world. 2-3 meetings were also done. Few people promised, and sometimes I find that something happened that I presumed the promises may work and promises doesn't work, and finally I failed to organize such a big conference for a giant of this functional analysis. We call it as a Banach. So let us start with what exactly the philosophy can be. Like Professor Vasil Virende, as he said about the Banach, few things I was also not knowing, few people he may not be knowing. This is possible because we interact with the people and we may not know many things. So when you look into the Brouwer's fixed point theorem, there are actually the result even before the Brouwer also. Historical fixed point theory is there, but later on they realize that what they are talking about, the solution is nothing but a fixed point. So Brouwer's fixed point theorem. So in Brouwer fixed point theorem, you know very well that it's a very simple and elegant proof, one line statement. So when you look the Brouwer's fixed point theorem, you will realize that the continuity on a closed interval is must, and then it promises that the continuous function is having a fixed point. It's not giving any guarantee to have a unique fixed point, and those days I think they might have not thought about that whether we should look on the uniqueness of the fixed point or not. So Brouwer has done, and after the Brouwer also, Brouwer did a lot of work, and as we today call it as a topological fixed points. Before the Brouwer, we have the Lipschitz condition also, and the Lipschitz condition, if I can write in the real line, then I can write in this manner: Tx minus Ty is less than or equals to L times of mod of x minus y, and this L is greater than or equals to 0, and x can be in x and y can be in x. Right? This one, if I say in view of the Brouwer, then T is continuous. So what are the main features in Brouwer? The first is the function is a continuous function. The second thing is closed interval, and we know very well that closed interval of R is a complete metric space. So is complete. So we have a result that every closed subset of a complete metric space is also complete. So another way I can say that they have the complete space. So F, then completeness, continuity, completeness, and they have the fixed point. Okay. Then Lipschitz is having this, that L is greater than equal to 0, and if I say same thing, translate in view of Banach, then I will say that this L is less than 1. So we have to understand why L is less than 1. So when you involve in the deep research and you try to do certain things, I think this is the human brain, they get the intuitions, that's true. Whether your result is going to be true or false or maybe in between. You get intuitions, that's true, we get intuitions. Many quarters we can understand that this hypothesis may have some result. Maybe in fixed point theory what we are talking about is some sort of concrete type of. Let me take some examples of Brouwer's fixed point theorem. Yeah, this is the example one I was talking about earlier also. When you look into this, the function is continuous and you can see that by applying the intermediate theorem, so intermediate value theorem, you have a fixed point. So we are not talking about any uniqueness of the fixed point, the function is continuous, completeness property is also there and you have the fixed point, right. So means is satisfying the hypothesis of Brouwer's fixed point theorem. Let us go for the next example. See this example. Our space is not closed, okay, is a semi. The function, you can see the function is a continuous function, it is a continuous function, okay. But when you realize that whether the function is having a fixed point or not, continuity is there, but the function is not providing us the fixed point. Other conditions I mentioned, some additional conditions, that whether the space is connected or compact or whatever it may be. If I am getting some additional features also, I used to write. So the space is not a closed interval, so even the function is continuous, we do not have the fixed point. Let us go to the next example. These are I am carrying for the past 20-25 years. Check the next one. Space is closed, closed interval is there, the function is defined, okay. So whether function is continuous or not, the function is actually split at the point half, okay. So what do you say about the continuity? I mentioned fine, but you have to know whether the function is continuous or not, you have to verify that. So function is discontinuous function, is not a continuous function. So one hypothesis satisfied, the second hypothesis not satisfying. So definitely suppose not to reach to the destination means should not have the fixed point. So not having the fixed point. Let us go to the next example. This is the example 4. Now look at this example. Both are closed, okay. I am making the union of these two closed intervals, and the function is a constant function. Every constant function is a continuous function. So is continuous. You have the Heinbold theorem for the compactness. Every closed and bounded subset of R is compact. So F is continuous, Y is not compact, you should know. Y is not compact. Draw on a real line and you try to understand that what is the gap actually. Why these two closed intervals are not compact. Any union of closed interval is compact. This is a question. So here you will find that is not compact, and later on I mention that connected also. So do this function have a fixed point? Yes.
When we discuss about fixed point,
So that
we usually work on self
Which one? Function? Yeah, what is the gap actually here? No, that you are talking about the self map always for fixed points, not necessary. You can have a metric space X with any metric, you have another metric space Y with any metric, you can have the fixed point.
Sir, we are talking about usual normalization.
Normally you write always X to X, but it's not necessary. There are many results available, but may not be working on that, you people, but it is there. There are good number of results.
At least the domain and codomain must have a point in between. Domain and codomain
Yeah.
must have intersection non-empty.
Intersection is non-empty. Here what happened? Intersection is empty. Okay. So do they have the fixed point? How they can? Okay. So they don't have the fixed point. Let us see the, so what happened here? So I say that is sufficient but not necessary. Okay. So the next example you see. Here is also the same kind. You can say what you are asking the question. Now check here.
So it is self-map.
Here they see your x is 0 to 1/3, 2/3 to infinity. Again 1/3 to 2/3. That part is not there. That part is not there. 1/3 to close interval 1/3, 2/3 is not there, right? Clear? Now you see the function. So x is not closed. See here, is not bounded also, is not connected also, is not continuous also. All whatever the hypothesis you need, none of the hypothesis is satisfying here. But what about the fixed point? It has a fixed point. It has a fixed point. Okay? Means maybe there are some results we are not even involved in such results. Like yesterday somebody is asking professor about the, I don't know whether this professor or someone else, so about the fixed points of the discontinuous maps. There are proofs, already proofs are available that if the function is discontinuous, it may have the fixed point. That is also possible. Okay. The Banach contraction condition has the beauty. So see here. So means
Maybe some typo.
where?
Infinity closed.
Yeah, it is typo error. Infinity can't be closed. Yeah, open is open. Yeah. No, infinity is open. It should typographical error. So I did not check actually so seriously this part. I closed that one because we use LaTeX. So that's why, that may be the reason. So see this one. So what exactly we are trying to draw from this, that this is Banach, this is Lipschitz. Okay, and what exactly the Banach has done in the Lipschitz, we have to assume the function is continuous, and what the Banach has done, he is deriving the continuity from the contraction itself, the condition or inequality itself. That's the beauty. So means we are not actually putting condition on the function that function is supposed to be continuous. You are deriving the continuity from the condition itself. This is what the Banach contraction condition speaks about. The other thing is, what is the actually the utility of this condition? Is it necessary? That unless we assume this contraction condition, then only we proceed for the proof. Where exactly the Banach has a problem? Because using the Picard's iteration, lot of people since for the past 3 days the same thing is going on, so you are well versed with the iteration schemes, particularly the Picard's, which is a initial of the iteration scheme. So the issue comes when you are trying to prove the convergence part. Even for the Cauchy, what about the Cauchy? So we have to think whether this condition can be removed or not. Your theorems should be in such a manner that if one of the assumption is removed, the theorem should fail. I am saying particularly whenever we write any result. Always I give the example of the Pythagoras theorem. Best example in mathematics is the Pythagoras theorem. If you say right angle triangle satisfying this condition, if satisfying this condition, right angle triangle. If you remove one of the condition, not satisfying. That's the beauty, the minimal conditions. And now these days what happen? Sometimes we don't care about the number of conditions putting on the theorem. Of course, Banach fixed point theorem, in the Banach you will find the strong assumptions, no doubt about it, for getting what? Uniqueness of the fixed point. For the uniqueness of, if I say fixed point and all fixed points are, if I somewhat I say okay fixed point, I got the fixed point. Because my destination is a fixed point, whether you are trying to obtain either topological or analytical or analysis through analysis, whatever it may be, I have a fixed point. But ultimately doing this much exercise, the heavy exercise, because of uniqueness, right? This is what. So now actually the last result motivated me to saying that sometimes it's possible that none of the features or circumstances favor us, but even though we are strong enough to face the situation to achieve our goal. This is the realistic, and sometimes we have to learn such realistic situations of some contrary examples. This could be one of the example that all the situations are against, even though they succeeded in getting the result. This I will talk about little bit later. So my main intention is, after this, see, this is the result of 1922, and after 1922 you know very well that in the world scenario there are so many things happen, not only in the context of our country but in the context of the world. We have 2 world wars in between. So the development of the mathematics, development of science and technology, development of many things, the operation research established during this time mainly between the world wars, because it was a need actually, optimization, okay. So by Banach, Lipschitz, and when you go little bit ahead, these are all the iterations, and people are working on the iteration side also, lot of iterations are there, and Professor Birende, he was talking about the iterations a lot, in particularly he is working, so I am not going into the depth of all such iterations like Picard's iteration, Mann iteration, Ishikawa iteration, Hong Kong Zoo slightly modified the Picard's iteration scheme. Okay, and after that you can find that there are good number of iterations. Now these days when I count, I think definitely 10-15 iterations people so far defined. So not in that context. Yeah. After Banach, I found most interesting part is like we derived the concept of continuity from the inequality of the Banach itself. So naturally, this is the phenomenal and natural question among the analyst mathematicians, that can we go little bit deviate this continuity part, and you can see that this is the result. R. Kannan, actually he is a student of Calcutta University, joined initially MSc in physics. Why he discontinued, I don't know. Actually I used to visit Calcutta University very frequently earlier, and he is a student of Professor B.K. Lahiri from Kalyan University. So since I had some interaction earlier, so I came to know that he discontinued physics and joined mathematics, and then the C. Yeah, he is R. Kannan, Tamilian. Okay, so his first result actually published in Bulletin of Calcutta Mathematical Society. I am referring the 1969 result published in Proceedings, but published originally in Bulletin of Calcutta Mathematical Society. So sometimes now in today's scenario, when you look into the even the general sections, right? So because of you only, because of your results only, generals are famous. And now these days what we do? Because generals are famous, let us send the paper to such generals. Because of general, I can also be famous. If my name is XYZ, my result is very good, I have doubt on my own result, and because of the doubt I feel that which is the best general in the world. I am searching such general and submitting my paper for publication to such generals. So see the scenario. The man who published his result in our own Indian journal and see the result in the world level. Same Banach also, that result is a part of his PhD thesis. How many of us are there that our PhD thesis is so strong, then that gets this much citations? Lecture is fine, but definitely I want to motivate you people that do something and is in you. You don't underestimate. Definitely you can do it. And out of these 24 hours, at least 1 hour, means 23 hours may not be working for you, but 1 hour out of 24 hours definitely working for you. Only you have to identify that 1 hour. That 1 hour falls in which period, that you have to identify. If you can identify, you continue with that hour, then you are also different. But once again same thing, like finding the best general in the world and trying to submit our paper into that general, same we are trying to find out the time which is convenient to me, not I am convenient to the time. See the result, so just a function is different. Now we are talking about the inverse function. This is what. So this is also one of the, I can say that most liking condition, inequality for me. And Professor B.K. Lahiri suggested me those days. I did my PhD in 1992, and these stalwarts were my PhD examiners. I think with professor we have the first interaction in 1989, I think, 88, 89. Since then, whenever I request, he is always there. So that matters a lot. So he suggested this, and I have included by coding his book to my PhD thesis, 2 examples, and many people they use the same examples. You have to cite, that is mandatory, is not your result. If your result, fine. If is not your result, at least you regard the person that this result belongs to this. This samosa is very good from this shop. So at least you should put a regard. So nothing wrong, and that shows your wisdom. So I have 2 examples, and somebody was asking from your side only, might be to Professor Virendra or Professor Veermani, I think, that which condition is weaker. Something they are talking about. They are independent. I am showing you the examples. This is the example, and these 2 examples I borrowed from the book of Professor B.K. Lahiri. Now he is no more. His son also retired from, I think, from Roorkee, sir, or somewhere, some university. So these are the 2 examples you can see, and you can find that the first example and then the second example. Second example, Banach, not Kannan. First example, Kannan, not Banach. So superficially we have not to learn such things. Go into the depth. What the mapping has made the difference between these 2 inequalities? Why the first one is right for Kannan, second one is not right for Kannan? Why the first one is right for Banach or second one is not right for the Banach? What happened with the mapping T? So that we learn later on, or we blindly presume that because of the continuity issue. We have to work out, even we know many things, we have to work out whether the term continuity exists or not. That's the beauty, that the first one, Banach, as I said, the inequality itself provide you the continuity of the function. The second one, not allowing you to pick the continuity, even it has a fixed point. And sir, now these days there are the data scientists, they are working on Kannan, not Banach. Yes, they are working on Kannan, because in data science what I say, see, I have the mathematical ideas, and in mathematics when we say real, do we find any gap between, how do we differentiate between a discrete point and the discrete and this real? I used to give a simple example. You take polythene, pour water, the water won't come out. I say this is real, and you pour water even in any of paper or something, and maybe initially may not be coming out, but after some time, yes, even our skin is porous because it has holes. So you can check the discrete and real in this manner. So when we talk about the real, what exactly the philosophy come into our mind immediately? We find that every space is filled with some dots, right? Some point, some numbers. And one more thing is, when we look into the Cantor's theory is enough to say that yes, how many numbers we don't know, how many powers we have to put, infinity to the power. So like that, the numbers are, the real line is full of numbers. But what about the data? Data never been finite. This is the reality of the world. This is the reality. How we can say that the population is infinite? We talk about infinity, but we never realize infinity. In the real life scenario, we only realize finite. Possibly, this finite also, because of the huge numbers, we are unable to count because of the population. So in data, during our period, means our lifetime, we may not count, but data can't be infinity. Not limited, I can say. Not limited doesn't mean that is infinite. So when the data is infinite, then how you are going to draw a continuous curve? So using such data, we are compressing the data or follow the data that we can draw a continuous curve. Means we are pressurizing, and we have the ability to change the nature of the data. This is what the data scientists used to do, because we have the limited thinking. We can't go beyond that in a limited time. But because of the student of mathematics, we are very easily can say that this function is continuous for all values of x. How? The question is, for all values of, you realize the function is continuous for all values of x? Because our study says that is also a data. Our study says that these are the functions, they are continuous for all values of x. But you try to realize them, you try to visualize them, and that becomes passion, and your research becomes extraordinary. No doubt about it, and you do wonders. And this is only the time when you are below 30, 35, you can do wonders. And don't feel only my professor will say something, then only I can learn something. Historically, there are the brilliancy, and that doesn't require sometimes the guidance. They require the inspirations, motivations. To do something, only someone has to, only you trust someone and someone says that, yes, go ahead, go straight, you reach there. And they trust. That's why I say the liking, disliking. If you like a person, definitely the theory becomes easier for us. This is my realization. I can assure you, whatever I say, I have the practical knowledge. And I realize this from my end, as well as I have very good data of the people so far we met them, and that too also different races of the world, not only this race, and different professors of the world, how they think. So we try to enter into the brain of the next, that how they can think. Why we can't think? Definitely there is some analogy. Sometimes differentiation comes, difficult to understand, but you try continuously, and if not 100%, you succeed up to certain level. These are the two. Let us go a little bit ahead of this. See the difference. There is something, no? So what is the difference in LED and this LCDs? The pixel powers, the partition system, the number of particles or points are very, very close. That's the reason that if you have the points differently, how to draw a curve, you can see the curve looks like the joining of the segments. Can this joining of the segments make as a smooth curve? This is possible in computers now. Yes, such things can be made smooth, not only smooth, I can make it as continuous also. These are the intuitions you have to understand. And in research, intuitions play a lot of role, vital roles. Be confident, use your intuitions, and don't discourage yourself. Someone if discouraged, you take in a positive manner. Okay, he says that I can't do, I can't understand. Because I understood very well that to convince myself, even professor is very close to me, you are also very close to me, if he tries to explain me some concepts, he can explain, but how do I understand? Unless I say myself that, yes, you understand this, you cannot understand. So you try to do not motivate. You motivate, even the negative thoughts comes or some negative power come against you to demotivate you. This is possible because this is the world full of sins. Now this is because that's why we call it as a Kali Yuga. You will find good number. Out of the 100, hardly you find one, hardly you find one to whom you can say, yes, I can understand. You can't. So you have to trust yourself. So this one, so this is also the part of when I was working. Later one result actually in between inspired me, and let me write that inequality and I will explain you how this. So this is one inequality everyone is using, those who talk about the fixed point theory. Okay, the T is a mapping from capital X to capital X, any space you can pick. I am not bounding this the space. So you have X, Y, Tx and Ty. Here you have X and you have here, I can say, image here, this is the transformation, X here, and this is the Ex. So these are the points you have, 2 points in the domain and the other 2 points are in the codomain. Based on these 2 points, they picked only 4. Banach picked 4 and Kannan. If you just analyze this, use the analytical method. So Kannan picked 4, right? So let me say like this. After Kannan, at the time of Kannan, only few people were working on the area of the functional analysis, particularly fixed point theory. But the majority of the people, they were working on summability, especially the Indian scenario as well as the American context. Europeans mostly, they are, even today also, they are more interested on the geometry side because of the schools. Schools means thought actually. We call it as school. School means a center of learning in when you talk about the synonym, but it's a thought. And they have some thought, like there are some institutions, they are famous for some reason. Like professor is from IIT Madras, it is famous for one of the some branches. This is because why you need the why you wants to get admission into this institution, because I want this subject. Like that, some thought is there for a each school, and each school is very concrete in their own way. So here you have this, and you can suppose if you generalize in place of 1 to 2, the question comes, the generalization has come after the Kannan, around after 1969, because as yesterday Professor Brinde was also telling, Professor Veeramani also told, mathematical reviews, and as he said, I was not knowing that part, that a person from Chandrabled, he left Germany and went to US. There are many, like one of my collaborator, Gerhard Zhang. I say Zhang, but he is not Zhang, he is Young, Gerhard Young. So he also from German, but settled in Bradley City, Illinois. So such I have also no idea. And mathematical reviews, definitely our teacher used to say, for 6 months you go and spend to search the reviews. I think you have also written. I have also written. She has, Manjusha Kulkarni madam also written. So we used to write the diaries and small pocket type, small tickets are there. It is written on those tickets that what the result. So we used to write the abstract of such results on these pockets, and suppose 100 results we have written the similarity. Suppose I want to work, professor says that okay, you go and work on the commutativity part, or you work on the area of the Brouwer fixed points. So I will go and search only the results related to Brouwer, and I will write the results or main result. It comes automatically, forgetfulness after some time. Those who do not forget, they become genius, and that is very rare. And the world is not running because of genius, world is running because of the average people, not because of the genius. Genius, yes, they are genius. We are going to derive their results, that's fine. So after 1969, that is K. Goebel, now he is no more. So some people started generalizing this, the mappings, generalization of mappings after 1969. I have seen some papers, that's why I can say this is available in the mathematical reviews. But their generalization is in this manner, This is the generalization. Okay? So you can think why this kind of generalization? See, this question has to come. Actually, whatever I speak today, at the age of 22, 23, I have joined my PhD, and what I was thinking, same I am trying to reflect today in front of you. So this is what, but there is a similarity. You follow strictly Banach proof, strictly only you need to define these two mappings using such Picard's iteration, one for even, another for odd. When you define, so you have the almost every part, you can reach till the end, that you have a Cauchy sequence, and because of the Cauchy sequence, the completeness of the space compel the sequence to be convergent. Okay. First we try to understand normally how to prove this completeness, and once we have the idea, then we say that make it compulsion to converge, this we say. So you get it, you get for one fixed point, you get for the other one also as a fixed point. When you get the other one also fixed point, so it comes like this. If one curve is like this and another curve is like this, then in such cases this intersecting point This started in 1969 onwards. Common fixed points. So far we are only talking about the fixed points. Common fixed points. Once again the question comes whether the common fixed points are unique or not. Maybe, may not. There are many non-unique common fixed points. Non-unique theorems are there. This Chirk has done lot of work. He used some minimization conditions also. And in Chirk's condition you will find maximum. So this is one way of introducing the map. What could be the another way? Anyone can? This is the one way I said. What could be the another way? At least I want to know from the two different maps. So actually G zoom is famous for this inequality. I don't know why the people not noticed earlier. I also did the same mistake what the others have done. I also followed the pattern. Later when I realized, immediate I have given a corrigendum and I included K. Goebel. K. Goebel already did introduce this in 1969, the same result, same inequality. But he was not able to prove, or maybe he left not interested to obtain a fixed point. He left with this condition, fx equals to gx, and we can call it as a coincident points. This is the coincident point. But the famous is Z. Jung, who has used, who generalized the condition of, sir.
Change the pink color is not there.
Okay, black is okay? Okay. This reflecting, I think. Okay. Now is okay? Yeah. Fx, Fy less than or equals to alpha times Gx, Gy. Okay, fine. This inequality I have now. Now what to do? The next. The next question is, if we follow the pattern of Banach, what the Banach has done, if I follow in that pattern, then definitely the next comes the iteration. How to define the iteration? So for such iteration, we require, this is first condition. So we require another condition, that is the containment of the ranges. This condition assumed in Jung's result for the construction of the sequence. You cannot just take it granted like can define the sequence using the Banach or Picard's iteration. So now you have the sequence also, you have the condition also. So up to what level we can reach when we have a sequence and one inequality? We can through up to Cauchy. Unless we exercise, we don't know, but up to Cauchy we can reach, I think. This intuition it says that we can reach up to Cauchy. Space is complete. So now the sequence is a convergent sequence. So if I say how the construction of the sequence is here, if I say let x naught is an arbitrary point of x, So definitely my point is like this, f of x naught. So this f of x naught is a point of fx. When f of x naught is a point of fx, so this fx contained in gx in this range. So definitely this is a point of gx. Then what happened? So I have to correlate with this. So how? For this point there exists a point x1 belongs to x such that f of x naught is nothing but g of x1. This is the construction. Then g of x1, right? This one. And what about this g of x is contained in x, because f and g from x to x. So again for this you have a point x2 in x, you again construct f of x2 and you have again g of x3 and continue like this. Other people, they used to write a new sequence also. This is one way. What the Billy Rhodes has done, Billy Rhodes says that you can assume the arbitrary point either in assume in x, but either you start from fx or you start from gx is not going to affect. He has given in one of his research paper after this, around 1982 I think, that is in contemporary mathematics. So this way when you construct, so ultimately what you have, now you have yn, if you presume yn as a sequence, so you have two types, one is, these are the subsequences y2n plus 1, another is y2n plus 2, odd, even. Both you can have. Construction of sequence is done. Convergence is done. Because of the completeness, you have the convergence. The next comes what? Fixed point. Once again same issue. You have what you have, you disturb the inequality. Then who will face the music? You disturb the inequality. You disturb the function. May not be space. So I am trying to show you that how much rich this theorem is just by disturbing two things. One is a function, the second one is inequality. You disturb both. When two things you disturb, in earlier I disturbed only one function. I have not disturbed much the inequality, but here I am disturbing two, inequality as well as the function, both. So naturally I have to assume this, and this is fine with the iteration. Now when such thing comes, again the problem comes about the fixed point. So before the fixed points, you are getting the condition something like this, fz equals to zz, coincident point. This kind of condition. So again you have to enrich the hypothesis, again demanding something, that I need some extra conditions, otherwise it is failing to move further. So I am step by step I am explaining why the conditions assumed in the theorem is necessary. So how the Jung enriched this, he presumed that f be a continuous function. You remember in Banach the function is continuous. So Banach says that you try with the continuous functions. So they extra assume the continuity of the function. In place of assuming both functions are continuous, there are some people they assume both functions are continuous but not necessary. It is unnecessary extra. That's why I say no, minimal conditions are required. And there are a good number of papers, they say they are wrong, with one condition is fine. To eat roti, one hand is enough. This is the minimal condition. If you get two is good, less energy, you can eat. So they presume continuity, fine, they reached, they obtain this. He did not prove this, I have proved it. Okay, he simply gets set and reaching the fixed point, because definitely he did this. Without that, why he presume f is continuous or g is continuous? So presume f is continuous and reaching to this condition. Again problem, Gobel has done up to here. Gobel's theorem says that f and g have a coincident point and left. He left with this. Might be not interested. Sometimes some people they think that others has to work and write their name as a citation. So this is a good idea of getting the citations from the authors. That you have to think how I can cite. And now these days Facebooks are there, newspapers are there, TVs are there to get the citations. This is also the way of getting citations. So that is the way of getting the citation, that you stop your results somewhere and write as an open question. But earlier people, they don't do like that. They used to solve from their effort at any cost. If they fail to do so, then they put as a open question. So what they have done, they 1, 2, 3 conditions over. First condition, second condition, third condition. Then they assume commutativity. Commutativity means Fg is equals to Gf. This is the generalization of the maps. They generalize the maps in this manner. Now, once they assume this part, they were in a position, he was in a position, this paper appeared where, you know, American Mathematical Monthly. So one can understand the publishing in American Mathematical Monthly is not so easy. This is just like a magazine of mathematics, 2-page paper. Very rare you can find in American Mathematical Monthly the place in that. If they don't find merit of the paper, simply they reject. Not necessarily that because of the volume they have to publish. It is like that. So once they have this, they enrich them. Actually the problem comes where, because of yn, they arrive this kind of situation, Fgxn. What happens if f is continuous? Gxn tends to z. I am hypothetically saying because the whole proof can't be given right now. If I say Gxn tends to z, so f is continuous, Fgxn tends to Fz. And when you apply this inequality, because of your right hand part, you get this kind of condition, and f is continuous. then there is a problem. F is continuous, G f x n, this only compel you to assume the commutativity condition, otherwise no need. Okay? This is the reason. So what they have done using the commutativity, they interchange the mappings GF to FG and they got it. They arrived at coincident point and finally they arrived at the fixed points, that is Fz equals to Z and Zz equals to Z, and once again repeating the condition, they have the uniqueness of the fixed point also. This is what, in my perception, Jung has done, and since he is my collaborator also, so we have done some good results. So after Jung results, another very good mathematician, Professor Silvestro Sesha of Napoli, Italy. This is 1976, and in 1982 he introduced another condition. Of course, in between lot of results, like sir was talking about Chatterjee's result, Professor's department, Das and Nayak, they have done lot of work. Das and Nayak also, Proceedings of American Mathematical Society, he also used the Jung's condition, 1979. He published that paper in Proceedings of American Mathematical Society, commutative map. And he used the Chirik's condition, generalization of the Chirik's condition in the lines of Jung. So you can find good number of results. So in 1982, what the Silvestro Sesha has done, later on, I think after my PhD, I obtained my PhD in 1992. He left fixed point theory, and in almost every of my paper, he was one of the reviewer. We used to send the pre-review. We never submit any paper. Never ever. We have the habit. Now this is trust is a problem now these days. Those days there is no problem. I never worked any paper which has come for the review. I never used so far such results in my any of the paper. Any. Like yesterday he was talking about 2 papers, right? And I was also talking about SP Singh from Canada and another one, I missed name. I will, that is a lemma actually. Okay. So he was a reviewer of almost all my review means my personal reviews. So we used to write thanks to him, and once he either SP Singh, either SL Singh, KL Singh, SN Mishra, and Billy Rhodes, these are all. We used to send them. If they say okay, we send to the, after that only it takes almost 3 months time. Then only we submit to the journal. And 99% no review. That is what our nature is. Means these days what is the mechanism? I will write the algorithm, based on the algorithm I will write a program, let the computer check, computer says that okay, then what happened? My program is correct. Computer says no, there is some error, my program is wrong. No, I will say whether my program is right or wrong. Who is computer to say? I made computer, okay, is a product of me, not I am the product of computer. Otherwise what happened? That one movie has come, Rajnikant's movie. Okay, the first one is machine learning and the second one is deep learning. I am teaching machine, machine learn, then machine teaching machine, deep learning. So this is the condition, and he has taken the Banach condition very nicely, utilized f, g, x gfx, and this is less than or equals to distance between gx and fx. But here the condition is for all x, like in the commutativity for all x. We have to mind such things. Why I like such type of professors is they understand the value of dot or points. One point satisfaction or all point satisfaction or many. Many is not all. Okay? So for all. This is 1982 Silvestro Sesha, this published in Publication Mathematica. After this, my collaborator Jung, I think my time is coming very near and near. Professor will say stop. Before that, let me talk about. Yes, this is the result due to Jung. This is the example. Okay, this is the theorem. American Mathematical Monthly. You can see T is a continuous function. You can presume anyone, right side or left hand side map, no problem. This is the Silvestro Sesha's condition, and it was called as weaker condition of commutativity, and he called as a weak commutativity. Later on in 1986, Jung has weakened, now Jung has the taste of commutativity, and I think for the next 15 to at least 10 to 15 years he used this condition very nicely, and the whole world is using even today. So he utilized this, and this is the condition that how the weak commutativity is weaker than the commutativity. Reverse implication is not true. The first implication is true, commutativity is weak commutativity. Then again what Jung has done, he has done this result. He removed right hand part, and he says that sequential commutativity, and the value is 0 at the limiting case. This kind of sequential commutativity he was talking about. But you see that there is a restriction, not for all x, see for some t, the converging point of f and g or s and t. Few days back, as I said, when I started working in 1989, and I submitted only two definitions. One is Young's compatibility, another one is my own definition. No example, these two definitions submitted. I thought, okay, let us go. Other people says that send to bulletin, send to Indian General Pure Applied here and there. She was also with me at that time, but I did not discuss with her. So I think you know very well. So I submitted directly without asking anyone to Proceedings of American Mathematical Society. And I got after 3 months 4 pages letter from the editorial board of Proceedings and rejected that paper. So, but that rejection has given me the, once again, negativity. It's a negativity. If I disappoint myself, oh, I can't do anything, this is my first paper, rejected, and this, I will start crying. That is not. Okay, they have given 4 pages. Out of that, I have drawn lot of things. And then I wrote a paper of 16 pages from that 4 pages. In between, I have the chance to meet my collaborator, Yul Jae Cho from South Korea, and Rhodes also from Indiana University, Bloomington. But Rhodes is, I find that his way of writing letters to me, as he is presuming I am a kid, And at the age of 22, he says kid means naturally I feel anger because one or two papers I said you have done this is not correct. If this you do this way, this is correct. So then naturally he felt and in a very aggressive manner wrote one-page letter along with some 40-50 papers to send it to me. So I sent to the paper to my, I thought better let us collaborate. So I sent it to Cho. So then again we discuss 3-4 months over. We have the problem like Kannan and Banach, how they are different. So we are unable to find a single example, counter example, a single example which shows that Zhang's result is different from my result. We failed to do, but finally we approached Zhong, and Zhong has given really a beautiful example. This is the condition we introduced in 1990. We submitted. This was actually accepted in one of the academic press journal also, but by the meantime this was accepted in Mass Japonica, submitted by Cho, and already he paid the publication charges are very high those days, and you know our condition very well, we can't afford the publication charges. So we have to withdraw the other paper from other journal. We withdrawn from that journal because publicly I cannot say which journal. So it was withdrawn, and this paper published in Mass Japonica. Still people are working on this paper, and this has got more than 415 or 25 citations so far. This particular paper, more than 400 citations, and still live. So this is what? This one. And after that good number of people, they have done tremendous work on this. In a similar manner, what we have done is, there was okay, I will just wind up in 5 minutes. I will give you one more. There was a lot of discussion on the non-expensive map. So if you refer one of my paper published in Glasnik Mathematica, is a very good journal. So in that journal, and you know the Grey Goose type of map, some sort of convexity is there in the condition. Okay, so we have proved in the Banach space convexity structure is there for this. So what exactly the condition is? The condition is like this: that Tx Ty is less than or equals to alpha times of norm of x minus y plus 1 minus alpha times of maximum of norm of x minus dx plus comma norm of y minus ty. This is the condition. If alpha is equals to 1, what will happen? Yes. This took 2.5 years to publish. And my collaborators are Professor Cho from Ganshang National Institute, Chinju, and one of, I can say, the best in fixed point theory of that era is Professor Brian Fisher from Leicester, England. He offered me postdoc in 1993-95. So this is the condition, and we worked almost together more than 1 year. We are reaching up to that the sequence is monotonic reviews, then you are very genuine, because for mathematical reviews there are the people who are reviewing the published papers. Negative remarks are also there if the paper has some problem, and that remark give bad impression. And if they find that this man is, they are not liking us and the result is also bad, then see the remark given by them is extraordinary bad remarks. You are not anywhere in that case. So by using that, almost I was sitting 6 months. I was at BHU, RA of Professor Shiv Narayan Lal, 93-95. So 6 months I was sitting morning 8 to evening, late evening 12 o'clock. In between lunch and dinner, few teas, that's it. Somebody asking, sir, where is tea available first day? So I passed through those eras. For researchers, if they are not having any the chewing habits, so tea is the only the drug for us to not to sleep till the late evenings. So that is the result that I could conclude myself to publish a paper in nonlinear analysis in 2000 when I attended WCNA 2000 at Italy, Sicily, Italy, where I was very fortunate to have my very good, you can say that mentor, teacher, Professor Billy Rhodes. I met him there and we have beautiful 10 days. We discussed a lot, and after that, that paper also published in nonlinear analysis, 10 pages paper, and that covers the almost the survey of, I said no, 6 months work. So survey of 1950 something to 2000 something. I have given such quote also, some guarantee quote. We have to give, otherwise some people, in my perception is fine, but others may feel, but till date, people are not even interested now these days to give such guarantee that whether you have, because I have gone through the MRs, that's why I can give with reference to the MRs. I can't give with reference to others. Now the web is full of papers, we are confused which paper to be used. So I am thankful for listening this very carefully. Thanks a lot, and thanks to Professor Veeramani.
Let us thank Professor Murthy for a very interesting and inspiring talk. In fact, many of you are expecting some examples for a map which satisfies Condon contraction but not Banach contraction,
yes.
And similarly other way. Also many other interesting results and many other interesting stories also, which to make you to get inspired. We do hope anyhow one more day is there, so we'll get some more interesting things from Professor Murthy.
Thank you.
And I also would like to again thank Professor Murthy for a nice talk, and you should ask at least one question. Otherwise, we will not go for lunch. Anyone? Oh, yes.
Sir, my question is, we have seen a lot of contraction mappings. So, as we have an example like a line equation, we have sphere equation like we have. So, we can use that formulae in programming. So, can we use all these contraction in programming coding? And we can make some application.
I think is possible, but I am not in a hurry to give any remark right now, because still I am in a learning stage of the whole mathematics in Python. Okay. But I do hope that it is possible. Like as I said, the issue is with the point. the issue with the continuity, because in the programming the continuity means they have some other assumptions also, and in mathematics continuity means we have absolute kind of continuity. So if you convert yourself continuity with reference to the data, available data, you can think of. But as you said about the sphere, already Gellert-Zong has proved in 1998, there is a paper published in Proceedings of American Mathematical Society on the unit ball using the compatibility.
And whatever we have a proof of theorem, sir, so can we correlate with the real life?
No, you don't need this much of proof.
Okay, sir.
Very short you can get.
An example also, sir, we have seen always examples like numerical
Yeah.
way. So we, I think, I expect
No, you cannot just hang on the system by putting the points between 0 and 1, something like that. You should be very specific, and in the Python programming we have to construct the sets at which point you wanted to check. Like in the real numbers also you are checking some points. If you simply say that check between these two, same issue comes, how many days it will take, I don't know. That's the problem. Yeah, because it will check each and every point. That's the reason. If you fix the point, yes, you check 10 points, 100 points, 500 points, even your data is suppose 1 lakh data. You ask them to check 1 lakh. Okay, you leave it, it will check and return the result after some time, or after some days, after some months. It will return definitely. It's possible. Yeah.
Thank you, sir.
Yeah, thank you. And any other questions, at least from MSc? Our teacher at least should be more free. Any question? Okay, if not, again let us thank all of you for listening right from morning to now. Oh, any announcement?
Yeah, there is an announcement. We are all going to the department, right, madam? Yeah, we are going to the department. I think the vehicle is available at the main door. From here we go to mathematics department. Our lunch is in the mathematics department. Wow, fantastic. Not here. Okay? So please proceed for the lunch, and we are supposed to be back by 2:30 here. 2:30 here, 14:30. Okay, and open discussion in 14:30. Okay? Thank you. Okay. Good afternoon, everyone. Sorry for the delay. This is due to departmental visits by our participant and experts to mathematics department after 1:15. So that's the reason that there is a delay of 10 to 15 minutes. Once again, we restart our afternoon session, that is the post-lunch session. Actually, in the morning I said, in the post-lunch session, the first session will be for the open discussion, oblique interaction with the experts to the participants. But at that time, actually, I had some doubts on Professor Brende. So that's the reason that I fixed it in the first and his lecture in the second. So he concluded his work, what he's supposed to finish off. So now I am little bit modifying, slightly changing. So this is interchange now. The last session will be the open discussion, and in place of the last session, this will be the preponed session. Professor Brende, he will talk on fixed points.
In ordered metric spaces, so fixed point, coupled fixed point, and so on.
Yeah, same thing, no? Okay. I had doubt. I worked a lot of work. Fixed points, coupled fixed points, and tripled fixed points in partially ordered metric spaces. Professor Brende will speak about, and I think my research scholar Rashmi, she has done lot of work and is a part of her thesis also. So that's why in her thesis you are also referred as a reference. So I would like to invite Professor Brende to deliver his talk and interact with the participants. Professor Brende.
Thank you. So there is a bigger event here. We are now a little bit small in comparison to the others. They pushed us here near the end. Will survive. So this time I want to speak about some other context in which fixed point theorems could be useful for applications. And the idea is to speak about these coupled fixed points, triple fixed points, and so on, multiple. Don't speak in detail about these topics, but just like in the other presentations, I would like to give you an idea of how we can always develop our theory to cover more aspects and more applications. And this is the main idea of my presentation. Gregg-Gush fixed point, it's a very interesting. Who studied this? Murthy? I had it in mind for a long time, but I was not able, I did not find time to have some insights in this. It's a very nice result. Gregg-Gush. Okay, what it's about? I promise you that I'll present you some words about this polemic between pure and applied mathematics. And here are the, I found the, so this was a great Russian mathematician, Soviet mathematician, Petrovsky. He wrote a beautiful book on integral equations. So one of the best books. We had it in Russian, in Romania. Unfortunately, it was not translated. I don't know if it was translated into English, but usually in Russia, maybe you know, some of you, at present, the American Mathematical Society is paying a lot of people just to translate journals which are published in Russian into English. So they contain very deep and serious mathematics, so the American Mathematical Society is doing this. They simply translate Russian journals. Russian do not care about this, so they write in Russian. Some now, the young people working in mathematics, of course, they are publishing in English, but usually they publish in Russian. So this is a proof of the great value of Russian mathematicians, very serious mathematics. Even now, I don't know the number of journals, but almost 10 journals are translated. And Petrovsky, he was a very special person. He said the following one in this polemic: what is important, pure mathematics or applied mathematics? And he said, don't discuss this question. They are equally important. And his argument is here. For if we would be dealing only with applied mathematics, then one day it will happen that we do not have what to apply anymore. So this, we have to do mathematics all the time, pure mathematics, to have what to apply. So this phrase is very important and encouraging us working in fixed point theory and applications to produce results, even if we don't can immediately show an application. So we just do results in pure fixed point theory, so theoretical results, and I am quite sure we someday will have the chance that some of the theory is applied in the problem. But it happens the reverse situation. From applications, we can get some suggestion what theory to produce. And coupled fixed point is such an example. I told you that originally the fixed point theory is coming from differential equations. Solving differential equations, this tool was extracted by Banach from the method Picard have used solving differential equations. So that's all. So the first fixed point theorem is inspired from application towards theory. Now we are usually going in the reverse sense. So we are going from theory to applications. Unfortunately, in fixed point theory, we are doing too much theory. So I have to be honest, I'm not happy with this. Sometimes we are doing too much theory, and sometimes some of these fixed point theorems are not relevant. In the sense, they just repeat. So they are not applied to unsaturated situation. So they are applied to saturated situation. And what we get is not new. It's just the repetition. So I just want to support Petrovsky's sentence by this situation I talked to you 2 days before, I guess. So it was a discussion, and I quote this great French mathematician, Dieudonné. Dieudonné means given by God in French. So Dieu is God, and donné is given by God. Dieudonné wrote a very nice book on mathematics, and in French is this title, to honor the human spirit. So he said mathematics is something that is honoring the human spirit. And in that book, he recounts this story about another great mathematician, Jacobi. You should hear of him, and Legendre. They said, Jacobi said that that some people consider that the unique aim of science is to honor the human spirit. And he said in French that a question for number theory is the same like a question regarding the system of the world. And this is the letter translated by me from French into English, and he's telling about Fourier's opinion. As I told you then, Fourier had the opinion that the main aim of mathematics is just the public utility, so to have immediately applications. And Jacobi says, no, he's not right, because the unique aim of the science is this very nice idea to honor the human spirit, and so he considers that a number theory problem is equally valuable to a question related to the universe system. And this was written more than 115 years ago, and he's right, because now, as I told you, number theory is everywhere in computer science. Here's the book. If someone is interested, this is the French version. It's a very nice music. In English, the translation is not very inspired, because this means to the honor of the human spirit in French, but here is translated as mathematics, the music of reason. I don't like this translation. So, coming back to our theory, our main aim here is to put theory versus application in fixed point theory, and to speak about how relevant its theoretical results. And I will show, I do hope I succeed to persuade you that sometimes we state a very complicated theorem based on several conditions, but in practice it solves very trivial problems, very simple problems, and its utility, if usefulness, is not relevant. And this is the case with the coupled fixed point theorem, and triplet and multiple and so on. I'm starting from these papers I produced 13 years ago, 12 years ago, on coupled fixed point theorems, and published, as you can see, in a very prestigious journal, Nonlinear Analysis. There were very well received papers, but in the end I realized that they are not extremely valuable. So what's the problem? So I said this problem of coupled fixed point theory is coming from applications. We have this system of differential equation. It's first order. U is the unknown and V is the unknown. And in the right-hand side, we have some expressions, nonlinear expressions, and also linear expressions. The same lambda for U and V, the same lambda for V and U, and you can see also the same lambda, lambda 1 and lambda 2 here. This is important. So this is a system of two equations, differential equation, depending on two unknown functions. And if we consider these boundary value conditions, we are working on the interval, I forgot to say, the interval 0t. So we are here, So we are asking for these conditions. So the solution will be, let's say, at the same level. This means u of 0 equal u of t, and v of 0 equal v of t. This problem, as we know, can be viewed in this way. A function u equal a function of u and v equal a function of v of u. And this is a coupled fixed point problem. And f, we convert in the usual way the differential equation into a integral operator form, and we get this this expression for f of u and v. You can see this kernel G1 and this kernel G2 corresponds to the two terms here in the right hand side. So in this way, our problem, and I'll write here because I'll come back to it, this is a coupled fixed point problem. So this is a coupled fixed point problem for the operator f. U equal f of u and v equal f of v and u. So this is the equivalent form of the system of the two differential equations. These are some details, how we get this, and what kind of functions, green functions, we are using here. If you are not familiar with this transformation, I would suggest you to read some of these papers. I'll put references. So this is the way we transform the differential system of differential equations into an integral form, into a system of functional equations. And here are all notations needed. So I want to say a few words about my philosophy of doing mathematics. I enjoyed when Professor Murthy spoke about the philosophy of doing mathematics. So I am evaluating myself, my own papers. Sometimes it happened to me, I take a paper I published 20 years ago, I just remember something about this paper. And I read it very interested. I said, let's say what I did here. And if I like it, in the sense is a pleasant reading, then I say this is a good paper. This is artistic impression. But I also ask for, in that paper, to have a clear statement of the problem, a clear statement of the new results, to have examples, as I mentioned, and applications. And I also ask for a very well documented paper. And sometimes, you know, it happens to any of us. I discover, I said, oh, this was the first time one notion or one result has been published. And after 5 years, 10 years, I discover this is not true. And so I changed the phrase. So I always says, it appears that the first, I don't risk to say this is the first, because we are not sure. So if it is well documented, it means this is title suggests to apply to matrix equation. They had some matrix equation, and no one of the methods they found in literature, let's say Banach contraction principle, other fixed points, could not be applied because they had some monotonicity involved in that problem. So they succeeded to find a very interesting theorem. I'll present you. Then two Spanish mathematicians, Nieto and Rodriguez Lopez, they continued this paper by Reorings. They applied to solve also ordinary differential equations, and the second paper is this one. And then very soon Bhaskar and Lakshmikantam wrote this paper, which was extremely successful in 2006, so 2 years later, 1 year later. So this, what did Lakshmikantam and his colleague? He just unified these two theorems, these three theorems actually. And what did Rahn and Reorings? They usually, in the Banach fixed point theorem, we have this condition. Let's say alpha, but for all x and y and x. So they changed this. They changed this, and they have weakened the requirement, and I'll show how. And they combine another interesting fixed point theorem, which is in ordered sets, is Tarski fixed point theorem. Tarski theorem is, has an algebraic flavor, so it's in complete lattices. In a complete lattice, if we have a monotone operator, so Tarski theorem says we have, it has a fixed point. And Rahn and Reorings unified Tarski and Banach fixed point theorem in this way. And how they did? So they consider on this space X a partial relation, and their idea was to ask this condition not for all x, y, but for all x and y which are in relation, which compare each other to the other. So this is their progress. And so that new theorem, which has a, how to say, an ordered and contraction type character, was very useful to establish existence and uniqueness results for various operators. And of course, it is possible to apply this kind of results to periodic boundary value problems and to other differential and integral equations. So here is the statement of Rahn and Reorings theorem. We have X a partially ordered set, so only partially, not total relation. D is a metric on X, and XD is a complete metric space. So this part, Professor Murthy said I can write here. I'll So this is coming from Banach fixed point theorem. This part, the other part is coming from Tarski fixed point theorem. So it is a very nice unification of the two fixed points. So if T is continuous and monotone, this is coming again from Tarski fixed point theorem, and this is coming to preserve the property from Banach fixed point theorem, because in the Banach fixed point theorem we know that any contraction is continuous, so it is necessary to have continuity. And the constant is here C. There exists a contraction coefficient C such that we have this condition. Here is for x in this relation with y. So y is less than or equal. He is not the usual inequality. Take care. This is the relation, the partial relation on the set x. Is not the usual complete relation, for example, on the real axis. And if also we can find an element x0 which compares to t of x0 in the sense x0 is less than or equal to t, x0 is in this situation with tx0, then maybe I have another line, and we have also from Banach fixed point theorem this statement. So this is a combination of ordered relation and metric relation. Very nice theorem. Very nice theorem. I'll go further. So this is 2004. Then, almost immediately, these two Spanish authors extended. It is important, the reaction. So sometimes people are reading all papers which are published immediately after they are published. Sometimes it is very good to do this. So they were the first to read, and they published these two papers. This was published later, but they produced at the same time. You can see they use contractive mapping theorems in partially ordered sets and applications to ordinary differential equations, and almost the same, but existence and uniqueness of fixed point in partially ordered sets and application to ordinary differential equation. In fact, they used in the first paper the monotone case for non-decreasing mappings, and in the second paper non-increasing mappings. So in the sense of the partial relation. So partial relation is involved in this monotonicity. I'll come back at a certain moment, and I'll show you these concepts in great detail. For the moment, I just want to tell you the following story. This was published in 2004, the paper by Gran and Raurings. But after a while, the mathematician, the specialist in the area, Professor Kamsi, by the way, Professor Kamsi, he discovered that the same principle has been established, you can see how many years ago, before this result. But this is a Romanian mathematician, very strong mathematician. His son is also very good mathematician, but his son is working in France, and he's in Romania. Why this result was not had no impact, because I'll show how impact had this theorem by Rane-Raugring. Huge impact. And this one, very little impact. Because this mathematician, Turinic, always he's writing his results in the most general and complicated way. So he stated the result not so simple like here, not so simple, sorry, because here is very simple, clear, crystal clear. We have a map, we have this contraction condition, we have this initial relation between the first two iterations, because this is the idea. This is x1, and so either x1 is less than x0 is less than x1, either x1 is less than x0. So this is very nice, but this paper by Turinic remained unknown for a while until Professor Kamsi told me, look, this famous theorem, because this is now famous. If you will look on this, the citation, it has hundreds, maybe 1,000 citations. Very cited paper, because it was very simple and people noted this result and continued to work. Then, what next? Bhaskar and Lakshmikantam unified the two papers I mentioned before, and they established a fixed point theorem. So I said, Nieto and Rodriguez did for increasing mappings in this sense. Then in the second paper, for decreasing, so this is U in this relation implies this, and U in this relation implies this. This is increasing and decreasing maps. And what did Bhaskar and Lakshmikantam? They took a map of two variables and introduced what is called mixed monotone. So is increasing with respect to the first variable and decreasing with respect to the second variable. And then they unified the results obtained by Nieto and Rodriguez, and they gave an application. Again, the history repeats. The paper by Nieto and Rodriguez had no very significant impact, but this one had an extraordinary impact. If you look in any database, I collected, I had a look just yesterday, it has almost 1,000 citations, this paper, almost 1,000. Very, very successful paper. Even if it is just unifying these two results by Nieto and Rodriguez. They just do this. So you see, all the time we should think what we can do. And they were very smart, very lucky to see that they can unify this into a unique map F, into a unique map F. Discover this result very late, let's say maybe 2010. I found the paper and I read, I said, these coupled fixed points are interesting. And I started to study. So again, I repeat the definition of a coupled fixed point. This time I use X and Y. So we have a map F defined on the Cartesian product of this set X. XY is a coupled fixed point if we have this relation. So look, this is related to the notion of fixed point for a map defined on a product. this Serbian mathematician, Presic, in 1965 considered such kind of mappings, and he established results to ensure that we have a fixed point. This means x bar is f of x bar x bar. If we compare this definition, what does it mean? It means that a coupled fixed point is a fixed point if x equal y. So in this sense, these results are also related. This was in 1965. Well, again, these mathematicians, Rahn and Reurings, Nieto and Rodriguez and Bhaskar and Lakshmikantam were not the first one to do this. So they were not the first one, and this is very interesting. The first paper on this topic appeared to be this one. Look, I found by chance, I read a little bit in Russian, but just a little bit, just to understand the mathematical text, and I was lucky that my elder brother was 4 years my senior, and when he started to study Russian, he was upset for his teacher, a lady. She was a neighbor of us. She all the time was telling to my mother, look, he is not good, he is doing this, and she was very upset, and she declared, I don't study Russian language. So he told me, I was in first class, he told me, please do my homework in Russian. So I started to do his homework when I was in first class, and this is the reason I learned Russian, and I can read any text in Russian. Maybe I continued some 3 weeks, maybe a month of doing his homework, and I just started to learn the alphabet. Russian alphabet is difficult to read, like Hindi. It's very difficult. And in this way, I found this book. You can see it is published in Russian, and we can see it's about nonlinear systemostatics. It used exactly the same problem. This is coupled fixed point problem. And he also published some papers before, and these are the papers he published about these coupled fixed points, and he combined it order relation on sets with contraction text. So he is at least so far I know that he is the first one to study coupled fixed point. But just in my papers I mentioned this name of Opoitsev. Opoitsev is the name of this Russian mathematician. And okay, I started to work on coupled fixed point theory, and here it's a kind of genealogy. I asked to one of my students to do this, and you'll understand how fixed point theory develops. Look, Banach established his fixed point theorem in 1922. Tarski, again a Polish mathematician, he's also from Poland, he established this fixed point theorem I mentioned you on a complete lattice. A monotone map has at least a fixed point. This is ordered fixed point. Please check. I sent Professor Murthy the file of this book, great book of Professor Rus, and you'll find there Tarski theorem and many other things. And then what appeared to be Rahn and Reurings unite is but Opoitsev did this, then Nieto and Rodriguez, but here I put Opoitsev, he remained unknown until I published some papers and I mentioned he was the first one actually. So you can see these years and how many? Well, lot of years. So 20 years after, more than 20 years, almost 30 years after Opoitsev was doing Rane rings. Of course, we cannot cover all literature on mathematics when we are documenting. And then Bhaskar and Lakshmikant this theorem in 2006, and I and my PhD student, we did in 2011 on triple, then with my friend Karapinar on quadruple, and then a lot of papers were coming. And of course, before this paper by Bhaskar and Lakshmikantam, he was doing the same thing for other classes of mappings, but only monotone without using contractive conditions. So this is the story of couplet fixed point theory till now. Then from here, it continued with hundreds of papers. So I like this, this diagram because it is very useful. I do recommend you when you want to systemize some results to do something similar. You will understand better the things. So we go back to the notion we need for our theorems for couplet fixed point. So we are in a partially ordered set. F, this set defined on the Cartesian product of x and x, has the mixed monotone property if F is non-decreasing with respect to x and is non-increasing with respect to y, which means this inequality. So x less than x1 less than x2 implies this for any y, and this one y1 less than y2, we say in relation to y2 implies this one. So this is a mixed monotone property. This kind of concept has been introduced by Bhaskar and Lakshmikanta. This, and here is the simplest example possible. This is increasing with respect with s, so is monotone, non-decreasing, and is decreasing with respect to y, and the unique fixed point is this point 2, 2. It's fixed point and it's also couplet fixed points. Another example is this one. So it is possible to have more than one couplet fixed point. And look, these are fixed points in the sense I mentioned. They are x equal y, but this is a couplet fixed point because x is different of y, and there is another one, the pair. So these are, for such a map which is mixed monotone, we have two couplet fixed points, well, actually four couplet fixed points, but two of them are actually fixed points. This is these are the simplest examples. So coming back to the theorem, I'll put all to read together. The merit of Rane-Reuring's theorems and of Nieto, Rodriguez, Bhaskar, and Lakshmikantam is that they combine monotony and contractive conditions. I will suggest you to think about, because some of your colleagues asked me yesterday or 2 days before a question regarding relation between accretive operators and contractive. And my answer was that Browder did this. Browder was the first one to show the relation between monotone type operators and contractive type operators. And it is known, for example, that monotony corresponds to non-expansiveness, strongly monotony corresponds to, and another property corresponds to contraction, and so on. So this is the merit. My idea is that here monotony is imposed separately of the contractivity. I guess some insights could be done having in view this equivalence. So the main theorem by Bhaskar and Lakshmikantam is this one. We have a partially ordered set, we have a metric D on X, and XD is a complete metric space. We have a continuous mixed monotone map F such that we have this condition. And you can see this is similar to the contraction condition, but here we have f of xy, f of uv, and here we have a distance between x and u and distance between y and v. Only for comparable elements, so only if x is compared to u by this partial relation and y is compared to v by means of the partial relation. Be careful, this symbol is not the same. I did not put, normally we should denote this relation by some index to differentiate, but here is the less than or equal is between numbers, between numbers because the distance is a positive number and so on. But here these are the refer to the partial order in this set X. And then if we can find a pair of points x0, y0 such that we have either this or this, then we are sure there exists a coupled fixed point of F in the sense we have this two equalities. This is the theorem by Bhaskar and Lakshmikantam, and we can look it in this way. What are the elements? I told you that it is useful to look carefully to some results, and you can do in this way. What are the mathematical objects and the main properties involved in this theorem? So these are a partial ordered set, a metric, complete metric space, an operator with two properties, mixed monotone and continuous, a contractive condition, and an order relation between the first two iterations. So in the presence of all these contract conditions, we get the conclusion. And here it's the application. How long can I be? Sorry, Professor, the time. How long? Until 4 o'clock?
Yeah.
Okay, so all right. Do not compress my presentation then. Yeah. So here's the, you'll have access to my presentation. So I just keep here. This is the result established by Bhaskar and Lakshmikantam. They consider this simple problem with some assumptions, and they succeeded to prove that if we have this condition 9, then the problem has a unique solution. And what to do with this theorem? When we read the theorem, we can try to weaken the contraction condition, to weaken the properties of F. All elements I mentioned before, the generalized, the ambient space, weaken the initial condition, extend area of applications, and to do various combinations. So this is the paper by Bhaskar and Lakshmikantam, and some other papers which were dealing with the two-point boundary value problems. I mention here just a few. Among them is this paper I published on this subject. There are many other papers inspired by this theorem. I put here just a representative of them. They were published, and several authors were applying the same technique to various differential equations. So I started to look on this theorem, and I tried to improve this. It was related in some sense with another topic we were studying with my collaborators, and in the end I asked myself, how large is the area of applications of these results? Is this theorem really useful in applications? And here it's a very elementary example. This is from my book. This example is taken from my book, I told you, Exploring, and so on. And this is a system of nonlinear equation which is not easy to solve if you are not familiar with special techniques. Here we have f, this function. F is continuous, is strictly increasing with respect to x, is strictly decreasing with respect to y. It has this point which satisfies these two conditions in the theorem of Bhaskar and Lakshmikantam. So the unique solution for 4 should be obtained by Bhaskar and Lakshmikantam theorem. But since the coupled fixed point is this one, y is equal to x is equal to y, we can apply this Prešich fixed point theorem, which was obtained in 1965. A second example, this one. I take this very simple function, which is mixed monotone, it's continuous, and we want to see if it fulfills the conditions in the Bhaskar and Lakshmikantam coupled fixed point theorem. So assume we can find such a k less than 1, and we have this inequality which appears there, and we are conducting to this, and we can see we get this contradiction 6/5 less than 1. So their theorem cannot be used to solve this simple how is y? This is a very trivial system, but their theorem cannot be applied to this because this condition, contraction condition, is not satisfied. What does it mean? It means that this contraction condition is too strong. So we should try to weaken the condition in the Bhaskar and Lakshmikantam. I go back. It's easier than to write on the whiteboard. Just allow me to go back to it and show you again this condition. This one. So this is the condition by Bhaskar and Lakshmikantam. This one. Okay. Now, I was trying to see what's wrong here. How could improve this result? Because it is easy to see that if we consider the coupled fixed point associated to this problem, I already wrote, we have a unique solution, which is the coupled fixed point and also the fixed point of this map. And this is the result of this investigation. So the result is an improvement of the theorem by Bhaskar and Lakshmikantam, and look to the conditions. X is the same partially ordered set, D is a metric, XD is a complete metric space, F is a mixed monotone mapping, nothing about continuity, you can see, there is nothing. So I drop the continuity condition at this moment. And instead of having that condition only this term, I added another one which is in some sense symmetric. And instead of considering k over 2, I consider just k, and because I have here two terms. And the rest of the theorem is exactly the same. If we can find x0, y0 in this way or in this way, then for sure we can say that this map, this function f, has a coupled fixed point x bar, y bar. This is the result. And now I want to see, to compare the two conditions. Sorry. This is condition of Bhaskar and Lakshmikantam, and this is my condition. What is the difference? I moved 2 in the left-hand side, so I doubled this distance, and I expanded this distance into two different distances. You see, dfxy fuv is here, and instead of the second distance, I took distance between the symmetric y to x and v to y, because the function is mixed monotone, so we can do it constructively. So this is the difference. K is also less than 1, and the progress we did is that in this condition, in this theorem, we do not ask continuity of the map of the function f. And let's take now the previous example. Our theorem applies to the example I showed you, and to which Bhaskar and Lakshmikantam theorem cannot be applied. And we use this. It is easy to see. We take absolute value and obtain this. We take the absolute value on the other expressions, and by summing up the two inequalities, we get exactly the inequality in our theorem, condition 13, with k equal 4 over 5, because we sum these coefficients and these coefficients, and so condition is fulfilled, and we have the existence of a coupled fixed point, because we can find x0 and y0 in this way, minus 3 plus 3, to which fulfill this condition. So look, this is an improvement. This is an improvement for sure of this Bhaskar and Lakshmikantam. And what is important to mention with regard of this new theorem? No continuity is assumed, and we get the same conclusion. And also, it is important to tell you, I proved this theorem by using a totally different technique of that used in Bhaskar and Lakshmikantam, as the technique was very natural. I just give an idea. I don't know if I have in my slides mentioned this. Let's see. This is existence and uniqueness. I did not include the proof, the idea of the proof. And this application, so I show you how I did. So I just took, translated this problem to a fixed point problem. Let's put not x, because I write here I have u and v. Okay, I'll put x u v and tu TV, and I converted this in such a, the notation is not very good, but I converted into a fixed point problem in this way. So I just applied the Banach fixed point theorem to this new operator in this way, and the conclusion followed. And these are also the improvement in the theory. This Bhaskar and Lakshmikantam asked for this condition, and this was this condition, and the two conditions are different because having in view just a moment, yes, no, this is the reverse. I was wrong. This was the condition in Bhaskar and Lakshmikantam, and B is from Berinde. This is my condition, and of course, this is a less restrictive condition than the other one. So it also improved the applications of this theorem to two-point boundary value problems. I have here an example to show, it's good what I said. So this is in Berinde, because this is 4/5 less than 1, and this is 6/5 is greater than 1, and this is the reason it does not apply. So there are many other developments. I just want to tell you another development in the remaining time. I showed this result to one of my PhD students, and I thought, look, this is a coupled fixed points. And he had a look on it. He said, why we should not consider these three sets and to define triple fixed points. Okay, I said, okay, but look, 2 factorial, so the permutation or 2 elements is just 2. So we had 2 elements, but permutation of 3 elements gives 6, and we need only 3. And the question is, which one from these 6 permutations, this combination should be taken into definition? And he said, I'll take this, this with red, and this he got to introduce this new concept, triple fixed points, in this way, and that is possible to have other combination. And we published together because he had a gap in a proof. I repaired it, and we published together. And this was what is called hot paper. It is extremely cited. A lot of authors consider them triplet, quadruple, multiple fixed points, and many other results were developed after this. And what was the problem? He proposed this definition for the triple fixed point. And when reading his draft, I realized it does not work. The proof in the case of coupled fixed points does not work, does not more work. So I discovered, and this is my contribution, I discovered that because of this Z, it doesn't work. So the final definition of a triple fixed point was this one. This is not, you cannot find in that list of 6, but it's the only way we can solve the problem. Why? Because here f is increasing in the first, decreasing in the second argument, and increasing in the again. So this was possible just changing this. And then here is the result. I mentioned for couplet, and for triplet we also consider some examples. And we were disappointed that enough because this is an example in our journal. I told you it's an example of a system of equation which is proposed to high school students, and it can be written as a triple fixed point theorem, but our theorem do not apply to this simple example. So our theorem is also not very large, and there are some other systems, so this leaves the possibility to define other concepts of triple fixed points using this kind of combination, and my student succeeded to why was this not good, this definition? Because from 4 solutions for 4 coupled fixed point, our theorem was able to catch only these two coupled fixed points, and not these ones. These ones were not obtained by using our, and so the problem was that we have this property increasing with respect to x, decreasing with respect to y, and increasing with respect to z, and working in this way, only these solutions are found. And if we have this, then we could get the solution. And what my PhD student did, he considered again the first definition, and he applied this, increasing, increasing, increasing in all arguments, and he obtained also very nice results which were published. So here is my list of conclusions. I read only a few of them. We should be aware of the fact that our theoretical results cannot be applied to very large classes of applications. As I've seen here, I've shown you here, some simple applications are not covered by our theoretical results. This means there it is room for improvement. So we should try to find other assumptions, weaker assumptions to find other theoretical results to solve this applicative problem. So we need more papers in fixed point theory with applicative part, and we should enlarge the area of applications. I did this in my previous presentation when I presented you the class of functional equations. So now if we go to see what classes of mappings, of problems are solved by using fixed point tools, we'll see mainly differential, integral, integral differential, and now fractional differential, fractional integral, and many other applications. We should enlarge this class, and once again I am happy to know that Professor Murthy is dealing with some applications to data science. I do believe in this. I know about some researchers working in this area. They are trying to apply in machine learning and in many other areas. I am confident in this. The Thailand researchers did a very nice work for applications in image recovery. In image recovery, Professor Swantai and his team, they did very nice, even in machine learning. They are working for a few years. So as a final conclusion for today, we should obtain as many as possible constructive fixed point theorems. This means a theorem that we can apply to solve a problem. concretely, so constructively. It provides us a method to construct the solution. So I'm in time exactly, sir.
Thank you, Professor Asil Barinde, and very nice presentation. And I think this coupled, tripled, and even n-tupled for odd and even, because I reviewed so many papers during 2010, 11 to till 18.
Yeah,
sometimes your paper also.
Ah, really?
Your paper also. Is now open. So my student worked. She worked. Yeah, we have sent a mail also during that time.
That time we have replied.
Really? I replied?
Yes.
Okay, thank you. I didn't remember. All right, I'm old enough to not remember.
So you are very wise even in your absence.
Okay.
So
Okay.
she worked on coupled and tripled
I
and
see.
n-tupled also.
Uh-huh.
Some paper published in this American journals. Yeah. Yeah, n-tupled also. Professor Imdad, he published initially for I think odd n, right? When n is odd. He published some paper on when in case of even, he published for n is equals to odd, not for n-tuple. Yeah, he published that one. So Professor Imdad also worked.
I know, I met him. I met him in Pakistan.
You met him?
I met him.
No, he didn't
Imdad,
go to-
he's not from Pakistan?
No, he's from AMU.
But
Javed-
it's a similar
his-
name
so-
in...
His name, Pakistan, Liaquat Ali Khan?
No, it's a similar name. I'm confusing, so these names.
Maybe.
Imdad, where is him?
He is from AMU, he is supervisor of Javed Ali.
Uh-huh.
Yeah.
In Aligarh?
Yeah.
Ah, no, I am confusing the person, but there is someone with I starting the name in Pakistan, in Lahore.
Javed, his name, one is,
He's also, I thought it's about him.
He's postdoc student.
I know.
Willie Rhodes.
I met also him. I met.
Mujahid Abbas.
I see.
He's Mujahid Abbas. He is from Pakistan.
Okay.
And we had some collaboration, and I know him very well. Yeah. So very good presentation, and I think professor has given nice things. And actually, those three people, particularly Bhaskar and Lakshmikantam, that paper in nonlinear analysis, I think the paper published in that. And they have given the idea of the coupled fixed point and along with the application in boundary value problem. That was the paper, right? Bhaskar and Lakshmikantam, two papers are there, Tenali Bhaskar and V. Lakshmikantam. And after that, I think you have taken up and we have also taken up. So it was like that. Any question from the audience? If no, we have the tea time right now, and there is one actually small change, as I said. So the change is in place of the open discussion in the first half. Now it is after the tea, open discussion will be there, okay, after the tea. So we three are here, and at 4:15 we start this open discussion. And for the books, you people said it is in my car. So you can go through those books. I will ask Uma Devi Patel madam to get the books from my car with the help of some students. So all the books are there. So you can see those books, and whichever book you like for the photocopy or something, you can take. There is one Taj copier is there opposite to road, or you can ask our this MSc students for Xerox copy. Okay, and most probably I shall try. Actually, every day I try, but it is a late evening, 12:30. So I miss many things. That's why I could not post the presentations of Professor Brunande. So, but today I shall try to positively do it. Okay. One more thing is you are actually attending for the past 4 days. Tomorrow is the last day, and you have to fill the feedback forms. So you will be given the each one of you is given 5 feedback forms for the 5 presenters. Okay, you have the names also, I think, and you are sent all the schedule every day. Please go through this is a GIAN group, and please submit your presentation, this feedback forms to Madam Dr. Uma Devi Patel positively by tomorrow morning, because these are very useful, and we have to submit the feedbacks to the GIAN National Coordinator, Hyderabad. Okay. So our link is available at the Hyderabad main portal, apart from our own. So anyone can see that, open that link and can see the YouTube, what is streaming, YouTube streaming. Live is going on, but after that you will find the recording forever. So along with this, you can find the YouTube streaming of 2007 October. I think it is also the same 23rd October started, and I think it is around some 28th October finished. Professor Dorel Mihach, this is. Okay, that is he is Suthep Sunthai. He is the student of Dompong. Yeah, so earlier only Dompong is the only professor in Thailand. He is the second professor in Chiang Mai University. Chiang Mai is in mathematics, yes. After that there are several private colleges. Now, like anything, now these days everyone is a professor, and in India, you know, we have many professors in India. No, of course, it should be. It should be. No, I'm not talking about the Thailand. In many part of the, yeah, not easy. Yes. No, I know that. There are many. In European countries, it is not easy. There are many, they retire simply even senior lecturer or associate professor. Even they don't go for the professorship also. Yes. Professor, for the Professor Zung, I have written the recommendations for his full professorship. You can go for tea break after 15 minutes, 10 minutes, I think. uncertainty over any issue related to your research, in the research at the international arena, and what could be the new avenues of the research. Like that I mentioned few things, formation of the groups, etc. Let me speak one thing, and then I will open the session right now, and with you Professor Brende and Veeramani both are there, me also present for the same. We have planned, yesterday we have discussed, me, Professor Brende and Veeramani. We are planning to edit a book of this 5 days GIAN program, and we welcome the articles on metrical fixed point theory and applications for that edited book, and most probably we consult Springer to publish the book. That is what we have decided yesterday, and we will check out that. Already checked out. I will plan, and after a thorough discussion with our experts, we will consult the publication agency, and once we get through, we notify all the participants, your supervisors, and other experts of the worldwide fixed point theorists. That is what we have planned. And if in this case, if the book comes out as a output of the GIAN, you are also benefited, as well as the funding agency also feel very happy that their outcome is excellent. The feedback forms are also given, or going to give, each one of you 5 forms. You have attended all the 5 experts lectures. Yesterday one lecture. Every day Professor Brende and Professor Veeramani's lecture. So please give your feedback, your I can say the opinion. There are few pages, a few pockets are there where you need to write. Please do write whatever you felt over here, going to feel for all the 5 days. Tomorrow is the valedictory at 3 p.m. and there are many who are leaving this station even before 3. So far it is difficult for us to conduct before 3, because once the valedictory is over, so very difficult to stop the participants to attend the lectures. Professor Birende is also leaving tomorrow at 9 o'clock. His flight is 8 something. So he has to leave. Positively he has to leave by 4:30 or 4 o'clock. So that's why. So once within half an hour, 40 minutes, this valedictory is over, and as soon as this is over, he will leave this place. And so with this, I shall take leave for this time, and please you present your queries, your problems, your research problems regarding anything, any problem you can ask. So one of you, I think, yeah, Apka, please take a mic. A mic is there. Please take a mic, and whomsoever wants to, I think it is there or here. Yeah, please. So those who are interested, they can ask. To Manjusha.
Sir, you have explained multi-valued and set-valued functions, but even though I have slight confusion, I understand that for set-valued function, graphically we get spiral kind of graph, whereas it is not true with multi-valued. But how mathematically we can distinguish both? Because in some books it has mentioned that both are same.
Then it's okay. In fact,
Both are same.
I do not know about so multi-valued map is symbol. Given an element in the domain, the image is a non-empty subset of a codomain.
Yeah.
It is just a subset. So that's it. In one natural way, for each x, the set of nearest point in general is a set value. X, the image is A is just a compact set. X goes to. No, you can, yeah, you can see it also, no problem. See, this you have seen, X. No, please sit it. I will write on that. X the metric space, A non-empty compact set.
Yeah.
So then, for each x in the domain, the nearest point, consider those elements in the set A, which is nearest
to
closer
the-
to x, such that distance between the point x and the set A equal to distance between xy. For example, compact means the function y goes to distance between y comma A, continuous. Continuous function on a compact set attains its maximum and minimum. So here we have to say here, so this is, we know that infimum of distance
Yeah.
between x and small a.
Yeah.
So then in general it is a set valued map. And we pointed out, suppose A is a non-empty, closed, convex subset of a Hilbert space,
Okay.
then for each x the nearest point is unique.
Unique. Okay.
And further, this maybe we will discuss tomorrow, it is non-expansive. Norm of, because this single one element, image, it is like f of x. P suffix a of y less than or equal to norm x minus y. In fact, this, what is enough is, A is a closed convex set,
Yeah.
then for each x in the domain, P suffix a of x is non-empty.
Yes.
Nearest point will exist. What is called strictly convex we discuss, that will give uniqueness. Single,
Okay.
But in general it's a multivalued map.
Okay.
That's why it can be any set.
Okay.
Image of, that's why if we say even from R to R, image of x can be a set. Okay, when you are telling say x plus 1, x plus 2, like that. Image of x is a set, that's all.
Okay.
Then we have used what is upper semi-continuous. I mean, image, that case, for a set-valued map, when that is continuous in some, we have discussed what is Kakutani fixed point theorem.
Yeah. Yeah.
K, compact, convex subset,
Convex subset.
T from K. Image of each element is a closed convex subset.
Okay.
Then that map is upper semi-continuous,
Yes.
if and only if inverse image of, you can tell anyone. Upper semi-continuous, if and only if inverse image of closed set is
Closed.
closed. In particular, if A is compact or approximately compact, the metric projection, P suffix A also upper semi-continuous. It is just image of X is a set. X belongs to the image Tx, then that case multivalued.
Okay.
Multivalued map as a fixed point means essentially distance between X and the image. Image is a closed set. Distance between X and Tx equal to 0.
Okay.
Distance between a point X and a set is 0 means what? X belongs to the closer. But closer is a closed set already, that means X belongs to Tx.
Okay.
I don't know, I'm not familiar with the other type of spiral or graph related to set valued. I mean, I don't think any graphical representation is there for. Selection is there.
Okay.
Under what condition? Such multivalued map as a selection. For each x, some small f element, small fx belongs to Tx, and that f is under some condition it is continuous. Like that, then single valued map we can convert.
Okay, fine.
Yeah. I don't know whether you are satisfied or.
Yes, sir. Satisfied.
Thank you. Any other? Same topic, anything else?
Okay, sorry. So I'll say. So the idea is that there are a lot of mathematical objects, we cannot figure them, we cannot represent them geometrically. It's ideal to have such situation when we can represent. Coming back to this, how to graph a multi-valued map, this is not possible, at least. So.
Particular, if we come to R to R, then if it is a selection.
Okay, so just a selection we can represent. But I just want to say how you work in four-dimensional space. We cannot represent, we are in a three-dimensional space. We are living in this and we cannot represent or draw a mathematical object in fourth-dimensional space, fifth, and so on, and n-dimensional. So some objects we should imagine, just and understand them without graphing. And here, for the multi-valued, in many fixed point theorems, we work with selections. Yeah. Selections are single-valued, maps attached, associated to multi-valued.
Sir, weakly compatible mapping, a strong compatible mapping, sir.
Yes. Difference. What is difference? How can
Weakly compatible mapping, and a strong compatible mapping.
Strong compatible mapping.
Yes, sir.
No, actually.
compatible mapping?
Huh?
Compatible mapping and decompatible mapping.
Okay, I can explain you first what is a compatible mapping. Actually, as I said in the morning, that the commutativity is introduced by initially K. Goebel, as I said, in 1969. But the fame goes to Gillard Young because of the complete proof after introducing the commutativity maps. So later on what happened, the generalization of the commutativity has come. Silvestro Sesha, as I said, from Napoli, he introduced weakly commutative, and I have shown you the condition also of the weakly commutativity. So this condition, the distance of STXN and TSXN, if this is tending to 0, whenever you choose the sequence xn in X such that Sxn, Txn tends to T for some, this is not for all, for some T in X. This is the compatibility. Okay. So actually what is the ultimate utility of the compatibility? So morning I was trying to explain you each component of the Zung's fixed point theorem. Okay. So in that component what happened? This component, okay, this component is helping you to obtain the first fixed points and later on uniqueness of the fixed points by using the whatever the contraction condition is given. So to proving this, what happened, this is T or Z you can say. So ultimately we are going to get the coincidence point. Bochera is there, he proved one theorem recently means some 15, 16 years over, and he has shown that this condition holds. If you carefully read our paper of Mass Japonica, we have given 3 propositions also, and we used continuity as a pivoting tool of such maps. So this condition, Szn equal to Tz, and ultimately what you need, can I have Stz is equals to Tsz? Here this is a coincident point, this is point of coincidence, and if you have S omega equal to T omega equal to omega, your fixed points are this, your fixed points are not Z. Coincident points are becoming the fixed points in all such cases, if you carefully read the papers. So what they have done is, Zung and Rhodes, they have written once again a paper and published in Indian Journal of Pure and Applied Mathematics. They were talking about the weak compatibility. Okay, what they say, this is compatibility. Okay, they say that if Sz is equals to Tz, and this implies that commutativity holds, then they say that this is weak compatibility. So they are means you can say the, like we say the AND users. So they are talking about the AND user part as a weak compatibility. But there are many other compatibilities also. Apart from this, as I mentioned, my condition along with Zung and Cho, what we have done is, we have split like this, Tsxn, Ttxn, this is tending to 0, and we are using AND condition here, and this distance of, Tsxn other way, and Ssxn, this is also tending to 0 under the same condition, this one, whenever xn be a sequence of x such that limit of Sxn and Txn equal to z for some z in x. This is compatibility of type A, we said. It is also later on we realize, after some I think 5 to 10 years later, we realize that because the fixed point theory is rapidly publishing like anything, we realize that even while proving, we don't need both conditions simultaneously. One condition is enough. But for our prepositions we need, whenever we try to say that compatibility of type A implies compatibility, and compatibility implies the compatibility of type A, in such cases we need both conditions. Okay, otherwise one condition is enough. If you presume that T is continuous, see the beauty, T is continuous, then you have this is Tz, and now you see this Tsxn, this converges to Tz. So you are getting fast, but it doesn't mean it is very fast, but you are getting this. So they call in this context as a weak compatibility. So like weak compatibility, they have the weak compatibility of type A also. There are many compatibility defined by many people like R.P. Pant, Professor H.K. Pathak, and there are many South Koreans, and then some Chinese, then Thailand people also. Sylvester Sesha of course did, and after his definition, weak compatibility, he stopped working in the fixed point theory and he shifted to fuzzy. So this is what? Sir? Huh? Yeah, there are many. There are many. I have given a survey also. In 2000 paper, this is published in nonlinear analysis. I have given the survey, and as well as you will find a algorithm also. Like he says that he is from the computer science background. So I have always the inclination towards algorithms and programming, etc. Of course, I am not from the computer science background. But I have such ideas in my mind always. So I always do such things in most of the cases. So if you refer that paper, so you will understand that such kind of things are given there, and you will find this kind of table. This kind of, today I am not getting much time, so I could not put the JPG file. And Professor Brinde is given some prediction. This is my prediction. This is my prediction regarding the where the mapping lies. And as on today, it is working in the same manner. I can say that. So if you have, yeah, you can take this paper. You can take the whole paper. This is in nonlinear.
I was using some of this.
Yes. Yeah. This is almost a 50 years, 50 years of reviews work. 6 months reviews in Banaras Hindu University when I was RA. So any other, is it okay? Yeah, okay, thank you. Any other question?
Hello. My question is Professor Vasily Brinde. Sir. Just out of curiosity, I noticed in your lecture that you remember a lot of mathematician names, his stories. I mean, how do you remember all of this? And second question, how one should, how much time one should take to read a paper? I mean, research paper, any research paper.
How long?
In general, how much time one should take?
I explain you how much time I can afford for research. So it's about 10-15% of my time. Well, sometimes I write a paper, a quarter of it now, then I leave it for half a year. Because of other activities, I take it back. Sometimes I forgot. I really forget about them. If I will show my computer, I have some tens of drafts. Some of them are 10 years old. So I just started, I abandoned because of missing time. So it depends. When I find something very interesting, so it happened to me with this couplet, fixed points. I wrote in 1 month 3 or 4 papers, really. But I was in the break between the 2 semesters, and I stayed 16 hours in front of my laptop, and after 2 or 3 weeks, I went to doctor, and because I had some problems, and he said, it's not from heart. Is from sitting and working to the laptop. So I did this foolishly. So I stayed 16 hours per day. I worked in front of the computer. So this is not healthy. I do not recommend. But it happens sometimes when the topic is very hot. So this you feel, also when I discovered each enriching technique, I was very excited. But after 2 or 3 papers, I said, it's enough. I leave others to work, and so it's a kind of saturation. So you cannot, but I know people who are producing. One of my colleagues in my university, he's really incredible. I don't understand how is he doing, but he's writing 30, he has just 2 or 3 collaborators, and he's mainly writing these papers, 30, 35 papers per year. I don't understand. So I can produce 5. So it's not a matter of, it's not a rule. So it depends on the time. Usually I work during the summer when I have no classes, when I spend some time with my family. Now I have grandchildren which are who grow enough to leave me to work, but some of them are not, so I can afford to work on summer. So during breaks. And the best way I work is leaving for 1 or 2 weeks my office to some university, and there I can work. At home is very difficult. That's the recipe to write a paper. But first you should stay and read and think many hours. So sometimes during sleep you can have a good idea, and that happens. Sometimes I'm telling myself, oh, how stupid I was 10 years ago. I did not realize this. And the final comment is that we have in Romania he died many years ago, a very famous writer. And he wrote a book about his childhood and the period when he started to write first novel. And he said, I realized that all the time I said of myself, wow, what a stupid guy I was yesterday. And I did this all my life. So it happens. This is, sometimes we do not catch an idea. And I explain some such instances. Sometimes we cannot catch an idea. Some people are catching immediately, some others not. So it depends on how committed are we to work. In my opinion, commitment is very important, to be devoted to this work and to work hardly and to be attached to this work. Are you satisfied? Okay.
Let me add one more thing. What he is asking is, so actually there is no hard and fast rule. Please be comfortable. There is no hard and fast rule that how much time you need. I told you, there is only one paper, and I was talking with Professor Veermani. For the past 25 years I am working, and I have no answer. 25 years. Whenever I get time, I work, but I don't get answer. There is one more incident, but this is true that a researcher conceives some idea, even in your subconscious mind, it is working. And if the problem is unsolved, it is working more. If problem is solved, it is not working more. I can give an example. If you can check in Hezbollah Journal, one paper accepted. For that, I can say that I went to home from my department. This is around 2008. And nobody is at my home. My family was staying in Hyderabad. I had good coffee and tea. I sat around 5:36 in the evening. I finished off my draft at 11 o'clock at night, handwritten draft. Morning I wake up around 4 o'clock. I start typing the draft. Again by 9:30 or 10 o'clock I finished. Communicated in the afternoon. Within 3 months published, without revision. Sometimes happen, we don't know. But this is not that one day you can write a paper. Actually this conceived long back. It is somewhere in the conscious mind, and on that day suddenly that evolve and says that you do this. Second thing regarding the remembrance of the mathematicians, only one thing I can say, not only mathematics, any subject. No need to, at least in 24 hours, morning also I said, in 24 hours time, you have 1 hour time. That you have to identify. What is that 1 hour time? And that 1 hour time, if you pay properly, what mathematician? Anyone can, possible. Date and volume number, page numbers, that is possible. This is all because the hard tradition of our teachers. And now these days, if we are very hard, so you see the classrooms.
So sorry, I have something to add this, but I have to write, because this discussion reminded me the following story.
Tell him Chidimu's story. That is the best story. Charles Chidimu.
Someone knows this name from graph theory. If you study, this is a Netherlands mathematician. He is still alive. I guess he's still alive. I'm not sure now. He constructed this famous algorithm. It's in graph theory. And it is about how you have a network, let's say, of cities, and you want to go and to visit all these cities, and you should do the shortest path, or maybe the shortest petrol consume, or any other things. And he was working in the what should be now Department of Computer Science, but it was in the 60s when it was no computer, just the first computers. He was the only one to work there. And he was studying this problem, how to solve, how to find an algorithm. And he's telling the story. He was engaged, and his girl, he took him for shopping. Generally, men do not like shopping, and ladies, they like very much. So for me, it's valid. I'm very unhappy when I have to accompany my wife for shopping. They would spend 10 hours in the mall, and I would spend 10 or 15 minutes, so no more. And he was accompanying his fiancée, and of course, when it's fiancée, you should be very, very gentle and very cautious. And after doing a lot of shopping, he was extremely tired of shopping, and he sat in a coffee and having a coffee. And he confessed, 20 minutes, he found this famous algorithm. 20 minutes. He was just had the, how to say, illumination. He just, but he was thinking about this long time. And it was just in front of the coffee, he realized this is the algorithm. Please check and see, it's a nice story. So this is the answer. We cannot give some recommendations. So it's particular to any person, how to do research, how to discover something.
Tell him about this ICTP. Yeah, that is good example. They can understand very well.
Which one?
Chiduvi.
Chidume?
Yeah.
What about him? Which?
His student story. How he is training the students.
Oh, good. I had a good friend, and I told you about him. Chidume. Chidume. Very, very strong mathematician. I told you something about, but yesterday evening I told Professor Murthy my experience with him and his scholars, MS and PhD scholars. I visited him in Nigeria, and he invited Takahashi, Goebel, Reich, me, and some other, and only me, there to go to Nigeria. I said, no, we don't go to Nigeria, it's very dangerous. I said, I have no any problem. I went to Nigeria, and I enjoyed this. And we had a class. I gave a course to his students, not more than 7, 8, or 10 students, mainly PhD students. And I presented some of my ideas. And one day, after a few hours, I taught these students, he came in the class. And he told me, Vasile, I want to show you what are we currently working. And he went to the blackboard, it was blackboard, and he was speaking about what I mentioned, duality mapping. In a Banach space, instead of inner product, we have duality mapping and something else. And he introduced this concept of demi-contractive mapping in Banach spaces. And he started, let us consider uniformly Banach space. What is a uniformly Banach space? Don't tell me you don't know. Okay. I need the concept of duality map. What is a duality mapping? Tell me immediately. Go to the blackboard and write. And this was his style. But believe me, his students were all bright, very well, working all night. Some of them, I could see the room and the lights. I was alone in Nigeria. I could see they were working hard. So this was very kind. This was Chidume.
Hard training paves a mode.
So it needed hard work. So he did this very nice. So he put them to work. I'm very kind with my students, unfortunately. I said, are you interested to work? Okay, work. If you are not interested, I don't force you. But in that case, the problem was he offered them fellowship, scholarship. So they were paid for that. So, and that was the reason he put them to work.
One more question. Thank you very much for your inspirational words. So I would like to ask with Professor Murthy, just highlight about the contraction, contractive, expansive, non-expansive, and quasi-expansive. What? Just highlight a little bit about contraction, contractive, expansive, non-expansive, and quasi-expansive, so that we can understand easily.
I think quasi non-expansive map, already he explained.
Yeah.
You remember? If you start with the Lipschitz map, from there only you have to start drawing when it is a Lipschitz map, then come to the contraction map, then come to the non-expansive map, then you remove one more condition, you have a contractive map, and what he has defined on the left hand side, that is the quasi non-expansive map. And when a quasi non-expansive map is a non-expansive map. So these are all the conditions. You have to start with the Lipschitz. Yeah. So in Lipschitz, L is greater than or equal to 0. In other, you can see that only coming up to the Banach, you have the constant. After the Banach, then you see the scenario. In non-expansive, there is no constant, means it is 1. And in contractive, it is strict condition, but that is not true for all values of x and y. You have to put condition on contractive map for x not equals to y, which is given by the Adelstein.
Okay, thank you. Thanks.
Sufficient condition is there for quasi non-expansive, implying non-expansive, anything is there?
No, I mentioned this. Here are non-expansive.
No, not table. Under what sufficient condition?
Okay, I'll write. This is what I say. So these are quasi non-expansive. And here are non-expansive with fix of T non-empty. So, and here are non-expansive with fix of T empty. So this is the relation. If it's non-expansive and has fixed points, then it's quasi non-expansive.
Yeah, if you restrict to the set
Yes, yes, yes.
Any other non-trivial?
I don't know that. So that's important because we don't care about this class of non-expansive mappings. They are not interesting for us. So in fact, we are interested only for non-expansive which have, so actually quasi-non-expansive. This is.
Clear or?
And lot of works now these days are quasi non-expensive.
Yes, yes.
Yes.
Sir, I have a question. Sir, like us, are you facing the problem like similarity and index with the other papers? Because most of the journals are asking for the similarity of the paper should be more less than 30%. So at that time, what you are doing, are you facing like this?
Okay, good question, and very, very actual question. So I am answering as a reviewer, as an editor mainly. Yes, this is a problem. A lot of journals are doing this similarity check. And it happened to me also. They say, oh, it's 30% similarity ratio, so you should decrease it in order to be considered. I don't like this kind of treatment. So a serious publisher looks into the paper. I mean, what to do, and I'll explain what I did to save such a situation. And maybe someone else can do this. People, what are doing now? To eliminate this similarity, we, in fixed point theory, we use T or S or U for a mapping. We use X, Y, or U or V for the variables. And what are many doing? Using strange symbols.
Yeah, that's true. This is the fashion.
So to be instead, I simply cannot read such papers.
No one can, sir.
Yes, and this is a solution, a feedback to such kind of journal that ask for reducing similarity. A serious editor and reviewer should look inside the paper. I had this situation. I did not change the notation. They said it's 30 and something similarity, because I had a definition for the article of Murthy, let's say. I had a theorem for another article of Veramani, let's say. And what to do? Believe me, I did the following thing. Instead of stating the theorem, I did some story about this theorem. So I described is this normal? This is not normal. So I did this. I said, Veramani theorem is establishing existence of, instead of stating the theorem. So this, I do not agree with this, but this is currently very, very often for journals. At my journal, I do not like this. If they are used very strange symbols, I simply send back the paper. And I ask, please use common notation in our field. It's easy after we read 40 years papers in this way. It's very difficult to go to Hebrew, some Germanic symbols to use instead of these letters. So this was the problem?
Yes, sir. Yes, sir. Actually, we are facing also.
Okay,
every time facing, and we are fed up. Like
this happens. This is not a solution. This is not a solution.
This is not the solution.
But this sometimes is useful. Instead of quoting the whole theorem, the whole definition, we should describe it. We should say the story of this.
Thank you so much, sir.
So it is losing the interest of the audience also to read such papers.
Yeah.
I used to send back, I am unable to review.
Yes, I very difficult. I do the same. I say I cannot review this paper because I cannot read with these strange symbols.
Yeah, my student comes their thesis, I say that original symbol you come, after that whatever you want you do. Very difficult, strange symbols. Yeah, any other question?
Yes, sir. So my question is related to a basic concept, sir. We study function, mapping, functional and operator. Are all are same, sir, or different?
Okay.
Map, function.
Okay. Functional should be considered. So, I am speaking about the terminology in our research group. In our research group, we call function just what we meet in real analysis. So, a real function, we say function. In that case, let's say f is defined on an interval, and this interval is in R, or we could be in R n and so on. This is function. When we have the domain space, we have the domain a space of function space, how to say, function space. So a more elaborate space, like in the case we have the continuous, the set of continuous map functions. Let's say x defined on 0, 1 to R. So this is the set of these mappings. So in that case, we say mapping, or operator. This is, in my opinion, the same thing. Okay, functional. Functional, this is classical. So functional means the codomain is R or C, and the domain is some linear space, some vector space. So this is typical. So this is the general way to adopt, but I've seen serious mathematicians telling function a map. It's not a problem. So it's correct. We can use it. But by tradition, so this is a kind of tradition. By tradition, I'll tell you the following story. In my university, one professor, engineering professor, he used to, in Romania, the marks are from 1 to 10. 10 is maximum, 5 is to pass the exam, and other 5 is the grades. So this is, and he was computing the grade, the marks for students, and he wrote 4.95, not 5. So he did this, 5. How is he was computing this? Sorry, this is not more working. So he was doing this, 495. And to pass the exam was necessary to put 5. No, he was not putting 5. And the same, some years. And the students complained to the dean, to the head of department, look, professor are doing this. And okay, the head of department asked this person, please, why you do not round this mark and give 5? No, this is 495. This is achieved, I put this. And in the end, the university throw him out. So said, you are not doing this, you go out from the day. He was left aside. Really, he lost his position. And then what he did? He started an action in justice against the university. And he won. After 3 years, he won this case. And why? in the Romanian law was written the grades are from 1 to 10. But the tradition, because this is about, the tradition was for 100 years to do this, to round the mark, to round from 750 even to put 8, from 860 to put 9, and so on. And in the law was written now. Now in the law was changed. This, and the law is now, it will be integer. So, but in the meantime he died. So, but he won the case, and he got back all the salaries for 3 years. The university had to pay him the salary. So this is tradition. This in the context. Sometimes we say by tradition some terms, but important is what is behind this.
Functional analysis, book like Alma, some cases, operator means bounded linear operator, continuous linear operator. Subspace means closed subspace. That is, they follow that because their interest is only that. Operator we don't just for any function, only bounded linear. That is just convention.
No, normally, normally at a school level, up to 12th we talk about the functions, because we talk about the sets, right? And once we start learning the group theory, linear algebra, then we start about the transformation. And once we enter into the these metric spaces and functional spaces, slowly in operator theory, we start, the same transformation is transformed into the operators. This also. And many times the students, they ask that why this is called a functional. Whenever I teach the course and I start with the non-linear spaces and their properties, till reaching the bounded linear operators, I will not say this is functional. These are all the basic requisite to know the functionals. And once you start the functional, means it is in your school term, it's a mapping. But here your domain is a space and your codomain is a set of real numbers or a complex number. Then only this is a functional. And ultimately from here onwards you have the applications, because already you are learned the linear algebra. So your applications comes to be the matrices. And matrices, as professor know very well, that in machine learning matrix is very, very important. Everything is matrix. We have to fix everything in the form of a matrix. So you have the applications also, transpose, then conjugate, all such things comes. So that's why the learning, this is today, but you have to make use of the pen and paper to explain yourself. Not you are going to write some exam. You are trying to, professor always says that we have to explain ourselves first, what the terminology mean. That is very important. And really in many journals I used to write, please remove this one. I was dead against this similarity check and other things. You feel that, okay, he copied and no citation, reject the paper. Ask them to cite the paper. If they are citing properly, they are not doing any injustice. If there are many people, they do injustice, they simply borrowed the idea of the others and writing the paper and without mentioning the references. That is wrong. This is plagiarism. This is the plagiarism. Plagiarism is a good word. But the similarity is a problem. In similarity, really very, very difficult. Using some new kind of terminology, some functions also now these days, xi, delta, these are new functions now these days, in place of S and T, F and G. So very difficult. Okay, any other question?
Sir, to prove fixed point, mostly first we prove that Cauchy sequence is convergent. So what for other ways, what are the other ways, and for that what literature we have to study?
If, for example, I told you for non-expansive map, we use Jones lemma. Like that many
So this constructive way to prove fixed point theorems works for a few. In metrical fixed point theory, almost the great majority is, but in non-expansive, even in non-expansive, which is metrical fixed point theorem, we cannot use strictly this. There are proofs which are non-constructive. So sequence of approximation is constructive proof. We take the sequence, we show it's Cauchy, but this not work. Even I mentioned Caristi fixed point theorem is in this class. Is not proved using the sequence of successive approximation. And it is very convenient. And the proof, the initial idea, I told you, is from Picard. Picard did the first one, this sequence of successive approximation, and Banach just transposed in the linear norm space. So this was, so it's a strong, I like these constructive constructive proofs, but some of the main results, topological fixed point theorems, which are very useful in a lot of cases where we cannot apply this fixed point theorem, are not constructive, are not proven with the sequence of successive approximation. We cannot prove because the assumptions are different. Yes, because we don't have sequence. We cannot exploit this metrical. We have this metrical condition, so it allows us to construct this sequence. Otherwise, we cannot. Yeah. This is fundamental also. So this is all right.
Sir, actually, I have one more question to Viramani, sir. Sir, we are talking about the topology about the space. So what is the meaning of topology? About the space. Yes, sir. What is the meaning of topology about the space, and how we can understand this is the topology, and it is not creating topology, it is having topology. Everybody says, but I need some explanation, sir.
No. Generally, if you have a non-empty set, some collection of topology means you have collection of neighborhoods.
Okay.
I mean, don't even right now don't. Ultimately, collection of neighborhoods. That neighborhoods have some nice properties. Then we call it is a topology. Collection means what? That neighborhood is, say that, that's what we say that capital X, a non-empty set, tau, a collection of subsets of X, that tau is going to be our collection of neighborhoods. Yes. See how it came, motivation comes from R2. In R neighborhood means we know center at X, some radius, open interval X minus R2, X plus R. We want to generalize just a set, see neighbors. We understand what is who are all my neighbors. So here these are all, to me, around these are all my neighbors. Okay. Like that we have a collection of sets. That collection will become neighborhoods. Then that collection, for that, you have some nice properties closed under arbitrary union. Arbitrary. Meaning is, you have any collection, script here, a sub-collection of the tau. Then the union of A blocks is script here also in the same collection tau. Okay. Then finite intersection. Yeah.
Question of Dr. Ruma is related to the metric.
Metric, that's what metric will, see, every metric space is a
topological.
We have defined, how to define an open set, every point, empty set is open, even using the definition. Capital A a non-empty set. When we say it is open, each point is a interior point. X belongs to A means that's what there is a neighborhood. Balls under at X radius are completely contained in A. Then we say it is open set. In fact, empty set also, even without X implication, X belongs to empty set, first statement. Not to make more abstract, we'll assume that empty set also open by definition. Then the whole space for every X, the balls under at X radius are is contained in X. So we have defined open set. Then what is the topology mean? Collect all the open sets. That collection is having these two properties, arbitrary union of members of that collection. We are proving that in
in topology we have done it, yes.
Set is open, finite intersection of open set
is open. Yes.
That collection, just to any matrix
Collection of
space,
neighborhoods, open sets, yes.
the collection of open set will become a topology.
Yes. Sir, I heard that complex valued metric space having no topology.
Which one?
Complex valued metric space.
Complex valued metric space, first metric space for a given X non-empty set, you are telling D a map from X cross X to C. Then how you define D of XY less than or equal to order relation all they have to introduce.
Yes, yes.
See, on any set, sparsely order or some, they introduce some notion. Then, no topology mean how to, suppose first, if there is a topology mean, have a collection, that collection should have this property. See how first it without?
Without open set you cannot.
No, open set we will define.
Okay.
No, like metric space. Metric space, no, what she is asking is complex
valued metric space.
Then what is the definition? Then, no.
For complex numbers, there is no ordering.
I mean metric, you mean D from X cross X to C.
C, yes.
Then what do you mean by T of XY less than or equal to some other XZ plus the triangle inequality? Can we talk? Can we talk about triangle inequality? D of XY a complex number. One complex number less than or equal to other two, sum of two complex numbers.
Yes.
That's why then you introduce, there are some order relation. Not, that's what even if we introduce many of the new generalized metric spaces, first you have to check whether the collection, we are introducing some, whether call it S metric or some other metric, whether that collection, that metric will induce a topology.
Yes.
Then only we can talk about closed set. Yes. Then they define complete, whether every closed subset is complete.
Yes.
How? I mean, we are using some term. Whether, suppose we are given a sequence, where it converges to an element. What do you mean by convergence? You need a, in which sense? Even sometime without defining topology, they will tell that with respect to that metric what they call. But whether it is Hausdorff, whether with respect to that definition, a sequence, it may be possible to converge, suppose xn converges to x, xn converges to y, x not equal to y. Our iterative method say xn converges to x means that is fixed point. Xn converges to, same xn converges to y, suppose if the metric is not a Hausdorff metric. Then how do you know? Then x is also a fixed point, y also a fixed point according to that. Then how you will get unique? I mean, any new concept, especially some metric, some type of generalize, you want to generalize the notion of metric. First check whether it is inducer topology. Then what type of topology? Whether it is Hausdorff, whether, then Hausdorff means every sequence will converges to a unique point. First countable means we don't require to go to net. First countable, then x is in closure mean enough to say that x belongs to a closure if and only if there is a sequence xn in A which converges. If it is not first countable, then you have to say that x belongs to A closure if and only if there is a generalized sequence which is known as net. The net should converge, then all those things. First you have to analyze all the things, even a symbol like similar to Banach contraction, but you are using there also closed, convergence, all the thing. But whether the convergence is unique, all those things we'll have to check. I don't know any.
Yes, yes, sir. Thank you so much, sir.
Any other? You want to clarify anything further?
No.
Sir, I have one question doubt, sir.
I'll give you something to read about, to be clear about, for example, in a B-metric space, if you know what is this, there are at least 3 different topologies. We can define the normal the usual topology by the B-metric and then other 2 topologies, and you can understand what is the difference between them. So, yeah.
Sir, my question is going to Professor Barinde, sir. And what are the real-life example of fixed point theorem?
What?
What are the real-life example of fixed point theorem? The
Real-life example of fixed point?
Yes, sir.
Sir, how many of you went out for after lunch? How many of you came back and sitting in the same place?
This is. I wanted to give you the cup of coffee, you know.
Yes.
If I do this, there is one point which remains at the same position. So they are moving around. So this is an example. This is an example of real-life fixed point. But this is a difficult problem. It's Brouwer fixed point theorem. There.
Yes, sir. Thank you, sir.
Think of real just for interesting, but understand the basic concept, why it comes. That's without knowing action converges to unique or not. You cannot just claim that the fixed point is unique.
Yes, sir.
Sir, in the last class, sir talk about the game theory. Game theory is
That's the motivation we give. I mean, how in a natural way we get multivalued map. Then using multivalued map, how we use for existence of Nash equilibrium point.
See, your hungerness means your diet. So every day you eat whatever you want, like iteration. Okay? So continuously you eat for 5 days or 6 days or 7 days. After the 7th day, the total volume of your diet is fixed. And whatever you eat within 7 days, that is only your diet. Divide, so average diet is the daily diet. Point is also the fixed point. That is also. Because after some time we also exhausted. So after how much work or after how much time you can spend on a particular kind of task. So when you are entertaining yourself, okay, your tiredness will be less and your entertainment is more. But when you use the brain work, and that too also not normal brain work, very heavy brain work, then you can understand that your tiredness is very fast. So you have to estimate this. So these are the problems beyond our, so now the computers are calculating such things.
Maybe about tomorrow we are going to discuss, already I mentioned, if it is a closed, bounded, convex subset of a Hilbert space, or even more generally, what is called uniformly convex Banach space, T from K to K non-expansive, then it has a fixed point, at least one. There, using Jones' lemma, will prove how we can prove how we are going to use it. Already we explained. Minimal invariant set, we told that invariant set is non-empty, contains exactly one element. And then the other, some other later. Any other?
It's a very, I think, stimulated session, entertaining session. Actually, normally I used to fix this every 4th day only, because all the 3 days are hectic, and normally the GIAN program is always hectic. Not only this GIAN program, Last time also what we organized is that is also very, very hectic. First day definitely you have less patience because sitting on one chair continuously for 6 hours to 7 hours. So that is not an easy task. But I tried to make you more comfortable. Even your sitting is also very comfortable sitting, not the benches like that. So anyway, thank you. And I say that thanks to both professors and our colleagues, our office, all the participating teachers, participating research scholars, our own MSc students, and definitely they are fond of having this photographs with the learned mathematicians. That's good. These are the memories. Even today, I am having the letters. Those days we used to write the letters. I am having the letters of Billy Rhodes. I am having the letters of Professor Brian Fisher. So all the letters are with me, and some of the letters are, mostly letters are motivating, because when we don't know each other physically, personally, but we know each other through the correspondence and some literature. So after some time we have some picture. That picture, it may not be exact the same picture, but we have the picture and we can gauge them.
In the correspondent itself, we can assume that.
Yeah, yes, yes. We are sharing the feelings also. Okay, so this time at least you do have the, what I say is good image also. But anyway, after the GIAN also, we are planning for a virtual group. We are going to form over here, and many professors, they will join our group. Of course, these two are there. There are some half a dozen professors are there, experts are there, who are experts in their field, and we shall try that every Friday or every Saturday, we should organize at least one lecture virtually on that. That is what, on Zoom platform. And this will continue the whole year. This we shall try. So we are planning, I am planning in this manner, and we have some people behind that, and I shall see that that part is done from my end. Thank you. Thanks a lot. Tomorrow we shall start our session at 9:30 morning. Okay? Thank you very much. Please fill your feedback forms and submit the feedback forms by tomorrow morning.